The lectures today will be a journey through the universe and back to the Earth. We will start by seeing how the Big Bang and the conditions in the early universe can be explored in the lab. We will then continue with planets outside the solar system, and see how we can employ the light from their star to study their atmospheres, and from there to say something about the planets themselves. And then we will go to the origin of life and see how the conditions for that, for moving from dead molecules to living matter, can be reproduced in the lab. After the break, we will go back to the Earth and be much more anchored to it. And so we will start looking at a series of natural phenomena which can have a high hazardous potential. And we will see how scientists are modeling them, simulating them, and employing huge amounts of data together with high performance computing resources in order to penetrate the complexities of the dynamics of such processes, understand their hazards, and ultimately mitigate the associated risks. And last but not least, we will be accompanied towards one of the last frontiers of exploration on Earth, which is represented by directly reaching magma inside the Earth's crust. So we will see how scientists are getting organized to get there, measure magma directly inside the crust in situ, sample magma from there, and we will understand why that can be a complete game changer for a number of reasons, going from understanding the origin of continents, developing the monitoring of the future for volcanic eruptions, down to developing and exploiting clean, renewable energy taken directly from the magma with a gain in efficiency of orders of magnitude. So that's the plan. And let's now rewind the movie and get back to the start in all senses, the start of the lectures and the start of the universe. So let me introduce you the first speaker. This is Máté Csanád from the Eötvös University in Budapest. Máté Csanád, Professor Máté Csanád, is a member of the Young Academy of Europe and is also leading the exploration of the early universe in Hungary, and also the participation of Hungary in the relativistic heavy ion collider, including a number of participation in projects and experiments at CERN in Geneva. Professor Máté Csanád has received a number of recognitions and awards from Hungary and from outside Hungary, and is also an enthusiastic outreacher. What I expect will make this presentation even more enjoyable. So let's go and start with Professor Máté Csanád and see how the early universe can be explored at the femto scale in the lab, which is 10 to the minus 15 meters, or for known scientists, 1/1,000,000th of a billionth of a meter. It's yours.
Thank you very much, and thank you also for showing up after yesterday's dinner. And first and foremost, thanks to the Academy for the opportunity to speak here. I am indeed. Oh. Does this work? No? Maybe I should try to use the...
This was working, but this one should.
Okay, yeah, this works. Okay, so thank you, and thanks to the Academy for the possibility to present here as a member of the Young Academy. I will speak about how we are exploring the Big Bang in the lab in particle accelerators with something called, a tool called Femtoscopy. and my subfield is focusing on Levy stable distributions, and we are in one of the beer capitals of the world, so I included a photo of a beer called Levy, which is named after something completely different. I actually repurposed my Researchers' Night presentation from a couple of weeks ago that I gave to students, because this is a little bit as an outreach. I see this a little bit as an outreach talk. And after this introduction, I will describe how we explore the Big Bang in the lab, and then introduce quantum statistics and the HBT effect to you, on which our research is based on, and how we explore femtometer geometry. This field is called femtoscopy, but it's not just femtometer geometry, but also very, very short time scales, millionths of an attosecond, which I just mentioned because of the attosecond related Nobel Prize earlier last week. Before we go into details, let me start with a quote from Feynman on how we understand or how we create new laws of nature. Feynman says that we first guess it, and then we compare the consequences of the guess to experiment or nature or observation, and if it disagrees with the experiment, then it's wrong. And Feynman says that this is really the key to science, at least surely to physics. And it doesn't matter how beautiful the guess is or who made that guess. If it disagrees with the experiment, it's wrong. And what kind of experiments do? We want to explore how the universe works, how its building blocks work, what their constituents are, and the situation is similar as if we couldn't look into a car because it's so small. We need to somehow take it apart, and the only way to do it, because it's so small, is to collide. It's maybe a blasphemy to collide such two nice old BMWs here in Munich, but nevertheless the point is that if we collide them, then their constituents fall apart, and then we can discover them. But the even more important point is that sometimes something comes out that wasn't there. Like I drew a bicycle there. If we do enough collisions, then sometimes just by chance, by something called the infinite monkey theorem in mathematics, something comes out that really wasn't there, that just formed by a very, very small chance. And another important point is that we need high energy to do that. There is something related, or the resolution that we can make is related to the collision energy by the formula written there at the bottom. I'm not sure if there is a pointer here, maybe not, that's okay. And it turns out that if we want to look at the proton size, then we need an energy that's called GeV, meaning 1 billion electron volts, equivalent to the energy of an electron accelerated through a billion regular small batteries. So it's a huge energy, and that's what we need to explore these small size scales. And what has particle physics accumulated as knowledge? That can be summarized in something called the standard model of particle physics. We now know that there are 3 main interactions: the weak interaction, which is responsible for radioactive decays, the electromagnetic interaction, which is responsible for everything we see around us here, the lights, the computer, the microphone, and the mere fact that we are not falling apart as a pile of sand, and something called the strong interaction, which is responsible for keeping the nuclei together, which only contain positive and neutral electromagnetic charges. So we need something stronger than the electromagnetic interaction to keep them together, and that is the strong interaction. All of these interactions have a carrier particle. All of these forces are mediated by particles, and those are the bosons listed there. One that is known the most is called the photon, which is responsible for the electromagnetic interaction, and the strong interaction is carried by a boson called the gluon. And, well, maybe it's not important to explain here at the Academy why it's important to explore something, why it's important to do basic research, but let me nevertheless tell that the story is somewhat similar to the exploration of the electromagnetic interaction. This was, well, discovered by the Greeks, but in a more rigorous scientific sense, it was discovered in the 18th century, and then detailed research was done, and nowadays everything in our lives, or a lot of it, is based on devices that are made possible by electromagnetism. In the strong interaction, the case is a little bit different. It was discovered in the 20th century, and at the end of the 20th century, or now at the beginning of the 21st, huge accelerators are being made and experiments are being carried out there to explore and understand the strong interaction. And who knows, maybe in 100 years, most of our devices will be based on the strong interaction. Nevertheless, already nowadays, it's put to use, for example, in something called ion therapy or proton therapy. What are the most important facts about the strong interaction? It governs particles called quarks, and it's mediated by gluons. The interesting thing is that electromagnetism has two charges, positive and negative, but the strong interaction has 6 charges, and the situation is similar to colors, where we have 3 colors, and if we add those 3 colors, we get something neutral. And if we add the 3 anti-colors, we also get something neutral, let's say white. And if we add the color to the anti-color, then we also get neutral. And in nature, only these neutral particles are seen. And for example, the proton is something called a baryon, formed of 3 quarks, green, blue, and red. There are particles called antibaryons. For example, the antiproton is also a baryon. That's formed of the 3 anti-colors, let's say, in this metaphor. And now we have a pointer. Excellent, thank you very much. Okay, perfect, thank you. Okay, so this is the proton here, this is the antiproton, and there are also particles called mesons, which are formed of 1 quark and 1 anti-quark. These are the main particles observable in the universe, and probably the reason for us discovering the strong interaction so late is something called quark confinement. We can remember how electromagnetism was discovered or first seen by the Greeks. They rubbed materials together and they saw that some charges are freed. We basically can take an electron out of an atom by force, and then we can see that charges are existing around us. However, in the strong interaction, it's not like that, because it's so strong. If we want to liberate, let's say, a strong charge, we have to put in so much energy that it materializes in a new pair of particles, a quark and an anti-quark, out of energy, and then it's closed again. Like you see here, if we increase the distance between a quark and an anti-quark, they are sometimes also lettered, and C is called a charm quark. It's not important right now. But if we take a quark and an anti-quark, increase their distance, then out of the energy, additional quarks are created, and again, the quark is confined into a neutral particle with an anti-quark pair. And because of that, we cannot free these quarks, and it's much harder to investigate the strong interaction. However, there is something that can be regarded as the opposite of this confinement, and that is called asymptotic freedom. And that means that if we have an immense amount of energy, a huge temperature, then quarks or colors, these color charges, can be freed. And the situation is somewhat similar as if we would live in a frozen world of microkelvin, let's say, and fluid water wouldn't exist. And then scientists would say that, well, we only see ice, but we can predict that water, fluid water, also exists, and we can experiment with it by throwing two ice cubes against each other. And then, for a fraction of a second, ice could melt, and then that water droplet that forms, it explodes. Of course, the little water droplets immediately freeze because of the small temperature, but out of the distribution of, let's say, those little ice droplets that we detect, we can deduce if this liquid material existed or not. And that's what we are trying to do. And the connection to the Big Bang is that these conditions, these ultra-high temperatures, where color charges were, if not free, but at least not confined into particles, that was present at the beginning of the universe. The universe is today, maybe let's say 14 billion years ago, and consists of galaxies and galaxy clusters and superclusters, but it wasn't always like that. It was only after the first 400,000 years when atoms formed. Before that, the temperature was too much for that, and it's only after the first 3 minutes when nuclei formed. And in the first microsecond, what was happening that we could call the strong interaction era, when this quark liquid, let's say, existed. And that we can create in the lab. You see here two ions being collided. They collide, then this colored medium forms, and then we take a photo of that with our huge particle detectors, and here is one collision. The time scales are such that the fluid forms in a time amount that we can call 1 femtometer over the speed of light, which is 10 to the minus 23rd seconds, and then 10 femtometer over the speed of light, it freezes out to conventional particles, and from their distribution we have to understand what happened. The facilities that research this are mainly the superproton synchrotron, the relativistic heavy ion collider, and the Large Hadron Collider at CERN in Geneva, and on Long Island at the Brookhaven National Laboratory. One quantity I would like to introduce is the center of mass energy, because it appears on some of the later plots I show, and we call that maybe the battery is out, I don't know. Anyway, we call that square root of SNN, which is the center of mass energy per nucleon pair that is collided, and that's maybe the most important quantity by which we describe what we are investigating. Okay, this works. Now it's back. So at BNL, there is the relativistic heavy ion collider, which is soon rebuilt to have the electron ion collider there. It's visible here. Different kind of nuclei are collided: protons, neutrons, helium-3, aluminium, copper, and so on, out to gold and uranium. Each has a separate reason why we do that. The most important is gold, because it's a very spherical nucleus and we can make nice collisions out of it. CERN, on the other hand, hosts SPS and LHC, and there the most important nucleus being collided is the lead, which is also nicely round. And we investigate those collisions, and the main goal of our subfield is to explore the phase map of quantum chromodynamics. Quantum chromodynamics is a theory of the strong interaction, And this phase map contains the temperature on one axis. Usually a phase map has some kind of a density. This density here we call baryochemical potential, is a complicated thing, but it's basically matter excess over antimatter. And the highest energy collisions are here near this axis, and especially the universe, when it was formed, it was very, very near this temperature axis, because there is only a very little matter excess. And LHC is here, and then what we see is that the normal matter is here in the lower left corner, and this quark gluon plasma or quark fluid is in the upper right corner. And what's very important is that if we decrease the collision energy, then we move on this phase map into this direction, and something that we are after is this special point here called the critical point of the strong interaction, and more accelerators are being built, and special programs are introduced at existing accelerators to have a scan of collision energies to map out this phase diagram. And one interesting thing that we are doing at Brookhaven is to introduce a gold target foil into the accelerator, and then have what we call fixed target events. You can recall how a regular event looked like. A fixed target event looks a little bit different, and I have a bunch of numbers here, but the point is that if we have some collision energy and we use the same beam of particles, but we don't collide two beams together as we are used to, but collide the beam with this gold target, then we can go down in energy to much smaller values. For example, at RIC, our main collision energies are in this range, 200 GeV down to a couple GeVs, and if we introduce this fixed target, then we can go down a little bit more, and this is very important in the exploration of the phase diagram, to that extent that a lot of new accelerators are being built. We are here close to, well, not so close, but in terms of country at least, to Darmstadt, where the new FAIR accelerator is being built and soon starting. And there are other programs, for example, the J-Park in Japan, and where there was the NICA in Russia, where of course connections are now cut. But there are lots of new accelerators being built to study this phase diagram, to collide particles with as many possible energies as there can exist. Now, focusing a little bit more on how we explore this, let me mention something called the HBT effect, which was discovered by astronomer Robert Henbury Brown, and he discovered a surprising discovery, or made a surprising discovery when looking at stars with two telescopes. He discovered that there is a correlation between these two telescopes, their signals, and this correlation actually reveals the size of the star. Stars in our telescopes, maybe not nowadays, but a couple decades ago definitely, were always point-like. So there was no way to see how big a star is, and it turns out that due to something called the quantum statistics, these stars, or the sizes of these stars, can be understood. And let me jump a little bit. Firstly, to mention that this effect that Henbury Brown discovered was understood to be impossible. And Henbury Brown said that if he knew that it was impossible, he wouldn't discover it. And that's why he says that ignorance is sometimes bliss in science. He didn't know that it's impossible, so he discovered it. And it's based on the fact that quantum particles are different from ordinary objects, let's say. When we have, well, I drew here 5 billiard balls, then we can ask the question, what are the number of ways we can select 2 billiard balls out of 5? Okay, it's 5 times 4 over 2, as we know from mathematics. And then we can ask, what are the number of ways we can select 2 photons out of 5? And then the answer is 1. It doesn't make a difference which photons we select. The question, which photon, doesn't even make any sense because they are completely identical. And this statistical issue that quantum particles are exactly identical makes the HBT effect possible. And what happens is that we detect 2 photons coming out of the star, and we could imagine that this photon came from here and the other photon came from there, and it doesn't make a difference if this photon came to that point and this to that, or the opposite, because the particles are identical, and these 2 possibilities mix in the quantum world, you could say it like that, and that creates the correlation. And this can be translated into particle physics, and the same happens when we look at a source creating particles in our accelerator of femtometer scale, which is absolutely point-like to any detector we can build, is several orders of magnitude smaller than what we could resolve. It turns out that if we measure correlations, then these correlations reveal the size of this little quark droplet that is formed there. The mathematical connection is that the correlation function, Q is the momentum difference, in terms of the momentum difference, is related to the Fourier transform of the source distribution that describes the probability of creating particles at some given location. Okay? So if we measure the momentum correlations, then we can understand how big the source was and what its shape is. It's actually very important what the shape is, and this is what I focus on. The central limit theorem leads to Gaussian distributions. Gaussian distributions are everywhere, and people assumed for a couple decades that they also exist in our little bang in the lab. But it turns out that there are phenomena which lead away from normal diffusion and from the central limit theorem, and then what applies is the so-called generalized central limit theorem, and it leads to stable distributions, or what we can call Levy stable distributions. This is an illustration. A Gaussian in 2D would look like this, and the Levy stable distribution would look like this. It's kind of opaque, like how you would see a light through an opaque medium, and this is not by chance, but because opacity is happening near something called the critical point. When critical phenomena happen, then correlations appear at all scales, and these create these opaque things. And another thing that creates stable distributions is something called anomalous diffusion or Levy flight, and this appears at many, many places in nature. For example, hunting of sharks. When sharks search for prey, they discover a region, but if there is no prey there, then they swim away. And so they don't do the usual normal diffusion, like particles here in the air, for example, but they follow anomalous diffusion, and climate evolution or economical processes also are based on this Levy flight. And for example, many might have heard the Pareto principle, where let's say 80% of the people or 20% of the people do 80% of the job, right? This is also based on this anomalous diffusion. And this is my last but one slide. What's important is that this shape of our distributions can reveal the critical point or the phase map of the strong interaction, and there has been predictions that the Levy index of stability has a special behavior near the critical point, and what my group does is to measure the Levy index of stability at various accelerators, and as last point, let me show this extremely busy plot that we are working on. We measured this Levy stability exponent at the SPS accelerator in an experiment called the NA61 Shine experiment, at the STAR experiment in Brookhaven in the US, in the Phoenix experiment, and also at the CMS experiment at the Large Hadron Collider. And these measurements of collisions of different sizes, the circles here are collisions of, or depict the collision size and collision geometry, show some kind of non-trivial behavior. And I actually have to close with that we don't know the answer to our main questions yet. We just opened this sort of highway, but this already took many, many years to understand this Levy stability exponent. But I hope that the picture clears in a little bit of time and we can explore this phase map with these type of measurements of femtoscopic sources. And with that, I thank you for your attention.
Hi, that's Lucarini from the University of Reading. I'm here. Yeah, so I also work on Levy flights, actually. I would like to talk to you later on. So I'm trying to understand what is the source of the jump process, because of course, you know, in a coarse-grained sense, Levy flights are a compound Poisson process. So basically nothing happens until something big happens, scaled by a certain, let's say, intensity index. So
Yep.
What is, in some sense, the mechanics, if you can explain it, of these, you know, it's almost like a charge oscillator. Something is charged and then released. Then you wait and something singular happens again.
Actually, my first answer is that we don't know. Okay. It's experiment.
Good.
But my second answer is that, of course, we have some ideas. And there are a number of reasons, but the most trivial reason is that this is an expanding source. Like, well, when we observe stars, they are not exploding usually, just normal stars, and they are static. But our source is exploding very, very fast, and there is something called the mean free path. There is a distance a particle can travel. And while the particle travels that distance, the medium exploded further. And because of that, the next step is even bigger, and there is no sudden change.
That's a compound effect, basically.
Yes, and this basically can create, as it can be simulated, this anomalous diffusion. So there is no sudden jump, but this increase, and because of the large mean free path, this can be created.
Okay, I will talk
Critical opacity is the other reason, and is kind of more important to us, but we don't know yet, so that's what we need to explore.
Thank you very much.
Yeah, my voice tends to be deep enough. And he's been also director of the Center for Space and Habitability at the University of Bern. And now he's chair of the astrophysics of exoplanets, or more or less that's the name of the chair. He's also honorary professor in a couple of universities besides this one where he stands, and he's honorary professor at the University of Warwick and UCL, University College London. What's probably most relevant about him is his book on exoplanets, which has been the second book ever on this subject, and which has been awarded in 2018 quite a high-level award by the Astronomical Society of America. So, please, Kevin, it's yours.
Können wir diese Lichter ausschalten, bitte? Hier. Es ist zu hell. this one, these three. Because my slides are very dark, and there's no point if you cannot see half my slides. These three. I'm sorry to make you wait a few seconds because I have a lot of dark slides and the information on them is critical for my explanation to you, so I don't want to give you a... Thank you very much. So I would like to start by telling you that we, the exoplanet scientists, are asking one of the oldest questions ever asked by humanity. Are we alone? This question used to belong to philosophy and theology. And now in the last 20 years, we have turned this question into a pattern recognition problem of Bayesian statistics and machine learning. And I'll explain to you how we scan the heavens to find out. So I'm a new professor at this university. I lead the new chair of exoplanet science, the first chair in Germany on this topic. And I arrived last August, and I want to tell you some of our thinking and activities. So what are exoplanets? Exoplanets are, is my volume fine? Fine. Exoplanets are stars orbiting our solar system. This feels very young. The first exoplanet around a sun-like star was found in 1995. Is too soft or too loud? Oh, you want to hear me more? That's fine. So the first exoplanet around a sun-like star was found in 1995 by two of my former Swiss colleagues. This is the reason I went to Switzerland for 12 years for my career. Didier Queloz and Michel Mayor found the first exoplanet, and they were awarded the 2019 Nobel Prize in Physics for this discovery. Ever since then, we now know of 5,500 exoplanets as of this morning, and the field continues to explode. What is really interesting is a question that belonged to philosophy and theology not too long ago, which is, what are the chances of finding an exoplanet around a star? Point to a star in the sky, what are the chances? 1 in a million? 1 in 1,000? Turns out it's better than 1 in 10. Who would have guessed? This is a measurement, not a theory. So the chances of finding an exoplanet is 1 in 10. They are very common, nature makes them. So what do we actually measure? I would like to tell you. So there are many methods for measuring exoplanets, but there are two workhorse methods, the radial velocity method and the transit method, which I will explain to you. So in school, you might have learned that the planets of the solar system go around the sun. Well, that's not quite correct. The planets and the sun orbit a common center of gravity. But because the sun is so much more massive than the planets, the center of gravity is inside the sun. And so the sun wobbles around the center of gravity. And so when you look at a star and you measure very accurately the spectral lines, you measure the wobble of the spectral lines. And the strength of the wobble depends on the mass of the planet. And therefore you can measure the mass of the planet if you can measure the radial velocity of the star very accurately. And Geneva are world leaders in this by 10 years. Germany is still 10 years behind on this topic. The other method is so simple, you can explain it to a child. So just look in the sky and just by dumb luck, some fraction of the stars will transit some fraction of the planets will transit their stars, and they will cause a little dip in the light, right? That's easy. So you see a little dip in the light called transit, and if you measure it regularly and it repeats, then it's a planet. Of course, life is a bit more complicated than that, but yes, for this audience, that's fine. What you cannot explain to a child is if you measure transits at different wavelengths. So if you have an atmosphere around the planet, and the atmosphere has water, there are some wavelengths where the atmosphere is transparent to water, right? So the transit looks a bit smaller, the planet looks a bit smaller. And there are some wavelengths where you're opaque to water, so the planet looks a little bit bigger. And it took my community 15 years to figure out how to do this. That they were not measuring noise from the star, that they were not measuring artifacts from the detector, that they were not fooling themselves with fancy Bayesian statistics. So the nutshell is it took my community 15, 20 years to figure this out. So let's make it a little bit harder. Atmospheric spectra 101. So I tell you that you can measure transit at many different wavelengths. And for the physicists in the audience, there's a mapping between the wavelength-dependent size of the transit and the cross-sections of molecules and atoms given by quantum physics. It's very straightforward, there's no tuning. The inverse problem is not so straightforward, I'll tell you in a minute. But what is astonishing, at least I find it astonishing, is that, sure, the planet can obscure the star, but the star can obscure the planet. So you can wait for the planet to go behind the star, called a secondary eclipse, and at that moment in time, you measure only the light from the star. And if you know only the light from the star, you can do a data subtraction, and you can figure out the light from the planet at all phases around. This is amazing, right? So I did my PhD in high energy astrophysics, and then when I saw this paper by Hedda Knudsen at Caltech in 2007, I thought, screw this, I'm not doing high energy astrophysics, I'm doing this. So I quit my PhD topic and I did this, because I thought this is so astonishing. We can do this now for 50 exoplanets and counting with the James Webb. So to make things less abstract, if Earth was an exoplanet, what would Earth look like? This is the famous photo from Voyager as it was leaving the solar system. Carl Sagan called this the pale blue dot, because if a planet was very far away, if Earth was an exoplanet, you wouldn't see all the oceans and the continents and the clouds, you wouldn't see any of that. What you would see is you would see a point source of light, meaning you get no spatial resolution, but you can split that light in different colors. And you can analyze those colors, called a spectrum. And since the patterns in the spectrum are given deterministically by quantum physics, you can figure out that the Earth has carbon dioxide, oxygen, ozone, methane, water, and so on. What is very difficult is to figure out how much water, how much methane, how much CO2. That's difficult, and I'll show you why. And the reason why you want to know that answer is because the classical view, which I think is outdated, is that if you can measure two molecules that show that the Earth's atmosphere is out of chemical equilibrium, you conclude that something interesting like biochemistry is happening. That's the classical view. I will tell you that this classical view is nonsense towards the end of the talk. So to summarize, what can we learn from spectra? Now I need to look at my slides. What can we learn from atmospheric spectra? We can retrieve chemical abundances. I use the word retrieve because the technical term for Bayesian inference in my literature is atmospheric retrieval. I'll show you examples, I'll talk you through it. You can retrieve the thermal structure of the atmosphere. You can infer the formation history from the inferred chemical abundances. That's a little bit more controversial. That's why it's in red. And if you can retrieve chemical abundances, you can possibly look for biosignatures, which are signatures of biochemistry. Again, that's a bit controversial. We'll talk about that. But what is not controversial, which my field is currently not paying close attention to, is you can infer from these chemical abundances the geological false positives of biosignatures, which is why Professor Dingwell and I have a very close collaboration on this, which I'll tell you about. So as I promised, here's an example. This is an example from the Hubble Space Telescope. There are many instruments on the Hubble Space Telescope. There's one instrument called the Wide Field Camera 3, WIF-C3. WIF-C3 was designed to look in the near infrared. This is just beyond what the human eye can see, because we know, again from quantum physics, that at 1.4 micrometers, there's a forest of water spectral lines. So if you detect water spectral lines, there's water in the planet. It's roughly at 1.4 micrometers, as you see. The spectral resolution is not high enough to resolve the water lines. You can do that from the ground using giant telescope, but that's another story. You can ask me during the Q&A. But if you detect this bump, which took my community, again, 15 years to not fool ourselves, you have detected water. And so the current state of the art is using Hubble. We meaning the community, not just me and my chair, have detected roughly 50 of these spectral features in exoplanets, more than the planets of the solar system. So this is yesterday's news. This is today's news. So 2 years ago, my community works very differently. We don't build labs in our buildings. We put all of our money together and we build a giant telescope that the entire community uses. In this case, this is a 6.5 meter gold-coated telescope that looks in the infrared called the James Webb Space Telescope. After delays of about 20 years and costing $10 billion US, it's finally in the sky. And the James Webb is the successor to the Hubble. And what's exciting about the James Webb is that it has many instruments and it looks across the infrared, not just the near infrared, but all the way into the mid-infrared. So in this case, this instrument is called near-spec prism. It looks from 0.5 to 5 microns. And the lines are not resolved, and this is not the best example, but this is the first example. I show you this because this was the first exoplanet that the James Webb looked at, and without doing much tricks of the data reduction, managed to get this spectrum. And what is exciting about this spectrum is you see water everywhere. Water is easy. Water is, I don't have time to explain to you why, but water is easy to detect. But you detect CO2, CO, let me say that in English. Carbon dioxide, carbon monoxide, methane, sulfur dioxide. For example, why should you care about sulfur dioxide? It turns out that sulfur dioxide cannot be easily made by equilibrium chemistry. You can only make sulfur dioxide via photochemistry, which is a disequilibrium effect. So this is the first detection of photochemistry outside of the solar system. Blows my mind, right? The laws of chemistry work the same outside the solar system as inside the solar system. So let's step back from these examples and look at strategy. So what's the strategy that my entire field is doing? So we have a whole fleet of telescopes. From space, from the ground, we measure spectra. As I explained to you, there's a mapping between the cross-sections of atoms and molecules given by quantum physics and the spectra we observe. And we would like to solve the inverse problem, the Bayesian inverse problem, called atmospheric retrieval. And we would like to give you atmospheric chemistry, which is molecular abundances. But we don't want to stop there. Once we get the chemical abundances, we would like to interpret what they mean. And we would like to interpret what they mean in terms of the planetary environment. And I'll argue to you that the most interesting question you can ask is that of the geochemistry. And I'll tell you why. So for those of you who don't think about Bayesian inference, here's an introduction to Bayesian inference, a layman's version. This is the layman's version of what mathematicians call Bayes' theorem. Right? You can have a debate with philosophers about whether probability is a frequency or a degree of belief, and you don't need any of that to apply Bayes' theorem. So what we are after is the item in blue, the probability distribution given the data of the molecular abundances and properties of the atmosphere. That's what we would like to have. In order to solve that from inverting the data, we have to define something called the likelihood. This likelihood is a mathematical term, it's not an English term. The likelihood is the mathematical relationship between the data, the model, and people forget, the noise. Very important, these three. The likelihood can be expressed on paper as a mathematical formula. You can always do that with lots of assumptions, but you don't need to. You can also express that partially through empiricism, through data, through measuring something in the sky. That's a detail. You can ask me if you like. It's a whole field called approximate Bayesian computation. I can talk about it in the Q&A all day long. And so after you specify the likelihood, you search the entire parameter space for all of the possibilities that make the spectrum you see. And in fact, this is something I explain a lot to philosophers. The fact that many combinations of thermal properties and chemical abundances give you the same spectrum. This is called a degeneracy. It's a feature, not a bug, of Bayesian inference. This is exactly what we expect. You should also be very clear about your prior beliefs, meaning, well, it sounds not scientific, but let me give you concrete examples what prior beliefs are. So for example, I believe that temperatures should not be negative. Chemical abundances should add up to 100%. There are less obvious prior beliefs, but this is what prior beliefs are, and the whole craft of Bayesian inference is to figure out what reasonable prior beliefs to insert into your system. After you have done all that, there's a very interesting part called well, there are many names. It's called the Bayesian evidence. Basically, when you have the likelihood, you can solve for something called the marginalized likelihood. You consider it over all parameter space, and you can compute something called the Bayesian evidence. The reason why you care is because then you can implement something called Occam's razor. So you have two models explain the data. Which is the model with the correct level of complexity, no more, to explain the current status of the data? That's Occam's razor. So you're penalized for models that are too complicated. So complication is not a good thing here. You want a model that is just enough to explain the data, not more. And when the data gets better, this then gets better. So the whole thing is dynamic. So that, in a sense, is Bayesian inference. How does it look like in practice? So you start with the data, which is a spectrum. You need a forward model. A forward model is basically a translator between the cross-sections of molecules and calculating a spectrum. You need to be very careful about your prior beliefs. You need to insert that in the sampler and the optimizer, which then gives you the posterior distributions, and you can do Bayesian model comparison, as I explained to you. So just to make sure you're not sleeping or I'm not boring, what is the most important aspect of this process? Take a guess. Shout it out. No takers? This is the most important part of the process. And this is what I teach my students. This is what the theoretical astrophysicist should know. You put in garbage, you get out garbage. The most sophisticated Bayesian statistics and machine learning will do you no good if your physics and chemistry is rubbish. Machine learning will not save you. So one of the first things we learn as theoretical astrophysicists is not to be fooled by our mental constructions. Here's one example of what an atmospheric retrieval looks like. So this is the example from Hubble, yesterday's news. So the data is in red, the WIFC3 data. The best fit is in black. It always fits, right? That's the thing about Bayesian inference. The model always fits, right? So if you put in a nonsensical model, it still fits, which is why you have to be careful about what you put in. And shown here in the contours are the joint probability distributions of different parameters. So the temperature, the water abundance. So the temperature is in red, the water abundance is in blue, the degree of cloudiness in the atmosphere of the planet is in purple. And these are the posterior distributions you see at the top of each of these quantities. So what it's showing you is that this planet the atmosphere is about 1,000 degrees. It has about 1% of water in the atmosphere, and it is kind of cloudy. It's amazing, no? We went from 1995, first exoplanet, to this in 20 years. We can tell you how much water there is in the atmosphere. Fast forward, today's news, James Webb Space Telescope. This is a spectrum from 3 to 5 microns. We can retrieve for the abundances of water, CO2, SO2, CO, and water, carbon dioxide, sulfur dioxide, carbon monoxide, and hydrogen sulfide. There's something there that I need to caution you about, though. So you see 2 sets of posterior distributions in 2 different colors. And the reason is because my community is finding out that when you use different procedures to reduce the data, the same data, and then you perform Bayesian inference on them, you get different answers. And in some cases, the answers are, in my mind, alarmingly different. But history shows us that we need to let this play out. So we need to let the literature play out. We need to figure out what's the problem with our detectors and our analysis methods, and this will play out. But again, this is just to show you that we are going to this process very sober. Why is geochemistry important? I promise I will tell you that. Geochemistry, so I'm going to switch gears now. So the first part I've told you about radiation, Bayesian inference, so I'm going to tell you about geochemistry now. I really like interdisciplinary research, and I think the only way you can do interdisciplinary research is if you convert part of yourself into that thing. So in the last 10 years, I spent a lot of time converting part of myself from an astrophysicist to an atmospheric scientist, and now in the new position at LMU, I would like to convert part of myself into a geochemist, like Professor Dingwell. So why is it important? The source is the source of atmosphere for small rocky exoplanets. I'll explain further. I've said many times, the outgas species are geological false positives of biosignatures. So just because you detect methane doesn't mean that it's from a cow. It could be from a rock. Same with oxygen. There are ways to make oxygen with no biology. I can make oxygen with photochemistry and atmospheric escape. Easy. So oxygen is not a biosignature. But what is, I think, most profound is that lifeless exoplanets with outgas atmospheres vastly outnumber the habitable ones. So the data set that we have for lifeless rocky exoplanets is 2-3 orders of magnitude larger than the ones we think are habitable. And that's the opportunity. That is the opportunity of the James Webb Space Telescope. So just to give you some background on this, this is one of my favorite papers when I was learning the field. The first author, Fabrice Gaillard, is a French petrologist, experimental petrologist. And I love this paper for many reasons, but one of the more trivial reasons is this figure. Because this figure shows you that the Earth started out with a so-called nebular atmosphere, hydrogen, helium, right? They inherited this hydrogen, the Earth inherited this hydrogen, helium from the sun, when the sun was young and forming. Then as time went on, the Earth developed a reduced atmosphere, carbon monoxide and hydrogen mostly. Then it developed a volcanic atmosphere. So there are world-class experts like Dingwell, Lavallée in the room. You hear from them about volcanic atmospheres. So water, sulfur dioxide, carbon dioxide. And then it evolved to the present atmosphere, the so-called mineral atmosphere, which is 80% nitrogen, let me get my numbers straight. 78% nitrogen, 20% oxygen, and trace amounts of water and carbon dioxide. This is the present day atmosphere. But you can see even from the Earth, it's not so straightforward to relate the mineral atmosphere to the beginning phase. It's really not so straightforward. And the atmospheric chemistry of Earth is mostly given by what the rocks are doing, essentially. You can ask this question of the solar system as well. Which of these planets have atmospheres that do not look like the sun? And in fact, the solar system has a dichotomy. And when I see this dichotomy, the question I ask is, does the solar system actually mislead us? And I'll tell you why. In the solar system, there are 4 gas and ice giants. And to an accuracy that satisfies an astronomer, these ice and gas giants have atmospheric chemistries that look like the sun, very roughly. So we astronomers don't care about percentage precision. We care about 50% order of magnitude, right? So to within the accuracy, not precision, accuracy, these things look like the sun. But we have 3 rocky things or 4 rocky things, depending on if you count Pluto, and they look nothing like the sun, even to an astronomer like me. So the Mars has a surface pressure that's 1 part in 1,000 of the Earth and is carbon dioxide dominated. Venus has a surface pressure 90 times that of Earth, is also carbon dioxide dominated. And Earth, I already told you, it looks nothing like the sun. So there's a dichotomy. But when we look at the exoplanet population, what do we see? We see a continuum of sizes between the Earth and Neptune, with no example in the solar system. We see objects that are slightly larger than Earth. They're very common. We call them super-Earths. They have densities that are very similar to Earth, 5, 6, 8 grams per cc. Thin atmospheres, probably, we don't know. We need the James Webb to know. So we don't know what they are. We also see things that are slightly smaller than Neptune, called sub-Neptunes. And they have very strange densities, right? So the gas giants have 1 grams per cc, the Earth is 5 grams per cc, and these things have 3 grams per cc. I mean, what is the object with 3 grams per cc? What kind of atmosphere is that? We have no idea. And that's the exciting scientific question. We have no idea what the lowest order scientific question, the answer to the lowest order questions are, the simple questions, the ones that make impact. And so the reasoning is that if you have secondary and primary atmospheres, and nature gives you a continuum in sizes, therefore there must be a continuum from secondary to primary atmospheres, right? And we don't know what they are. So we started calculating this. This is the cartoon. So the top channel is the solar system channel for the rocky planets, right? So for whatever reason, the planets have lost their hydrogen, and you have outgassing into basically, well, the outgassing is dominating the atmosphere. But nature suggests to us that there's a second channel that doesn't exist in the solar system, which is that for whatever reason, this planet retained a very thin hydrogen atmosphere. So not 100 bars for the atmospheric experts, but 0.1 bars, 1 bar. It's possible. It's possible to tune the mass and gravity of an exoplanet according to the laws of physics to get something that will retain a hydrogen envelope, and nature has examples of this. And so if you outgas into a hydrogen envelope, what do you get? turns out it's not a difficult problem, it's a thermodynamics problem. It's a mixed phase thermodynamics problem with non-ideal gases and non-ideal mixing for the experts in the audience, but you can calculate it. So I calculated this with one of my staff scientists in my chair. He's not a physicist, he's a computational geochemist. And the message is that, and the vertical axis is the abundance, and the horizontal axis is how much hydrogen the planet had when the outgassing happened. This is very difficult to calculate, how much hydrogen you have, because it's the balance of two processes I don't know how to calculate. So, the message is that a rich chemical diversity is possible. So how much time do I have? A few minutes. Yes. So I'll skip the last example. So the point of this slide is that just using simple thermodynamics, I can produce a whole zoo of atmospheric chemistries that's not seen in the solar system. This suggests to me that it's very interesting to point the James Webb at these objects and just see what we find. Just be surprised by nature. I had a case study where we actually have data on this, but I have no time to show it to you. So let's end with biosignatures. What are biosignatures? This is the exoplanet definition of biosignatures. I know geoscientists have a different definition. These are long-lived gases, providing not solids, not liquids, because we can't detect these, providing robust evidence of biochemistry. The key word is robust, which accumulate in the atmosphere in sufficient amounts. This is also important, because if you don't accumulate in the atmosphere, it's very hard to see it. To be remotely detected by astronomical telescopes. Remotely because we are not flying there. These things are very far away. It would take centuries to get there. And there's a vast literature on this, a very confusing literature, some of it very Earth-centric, some of it not. But one of my favorite authors the authors of papers to read is one of my mentors, Sarah Seeger, who I consider one of the true astrobiologists. She's a professor at MIT. And if you read her papers, then you get messages like, dimethyl sulfide, DMS, is a good biosignature because we do not know of a non-biological way to produce it. Methane is not a good biosignature because we can easily produce it using rocks, using outgassing. And I'll leave you with two messages. Academics are usually very measured in our words, but I will not be measured because I want you to understand this. The classical view is that there are magic molecules that I can search for. What I mean by that is I can build a $10 billion telescope just to look for oxygen. This is a very bad idea. And the modern view is that this is nonsense. There's no other way to say it. It's nonsense because whether a molecule is a biosignature depends on the atmospheric context. So whether an atmosphere is reducing or oxidizing, what the background molecules are determines what the biosignature is. So there's no magic molecule, and this is the reason why I chose to dedicate my career to the atmospheres of exoplanets. This is the reason why. The atmosphere is everything. And this is the vision that we are trying to fill. There's the astrophysics of exoplanets, which is very established. There's something that people like to call astrobiology, and they throw this word around, habitability, which means nothing to me. I think this field doesn't exist yet because it has a sample size of 1. And this field would like to study biosignatures, but I think we are jumping the gun. I think there's a step in between called geoastronomy, the marriage of geochemistry and astrophysics. And the reason why you should care is because in order to understand biosignatures, you have to understand the geological false positives. There's no way around it. You want to make an extraordinary claim, you need extraordinary evidence and understanding. And after you do this, then you design the $10 billion telescopes. And the vision behind this is that I firmly believe that future generations of exoplanet scientists cannot just be physicists. You cannot understand the natural world using just physics. There's no way. I can debate you this for hours. You need to learn some chemistry, you need to learn some data science, you need to listen to philosophers of science. And this is the reason why Professor Dingwa and I will build this new Munich center called the Center for Astrophysics and Geosciences of Exoplanets. And we'll spend the next 10 years studying this. Thank you very much.
Thanks a lot for an inspiring talk. There is time for one very quick question over there. Yeah, first one. Yeah.
Oh. Thank you, that was a fantastic talk. I have 3 really dumb questions. The first one is you said 10% of the stars around us have exoplanets. Can it be that we are under-evaluating that because of we are using the transit methods? Then you mentioned the atmosphere of...
Sorry, can you repeat the first question? I didn't get it.
Sorry?
Can you repeat the first question? I didn't quite get it.
Oh, you said 10% of the stars around us have exoplanets. Can it be that we are under-evaluating that number because we are using the transit method to detect stars that are transiting in front?
In fact, absolutely. So just to answer that question, 10% is a conservative estimate. And there are estimates as high as 50%, but I don't buy them. There are extrapolations, but 10% is a very conservative estimate.
Okay, and a very dumb question about the atmosphere. You said that what you see in your experimental results is atmospheres that seem to be standing in between the two types of planets that we have in the solar system. Could it be that what you see is a compound of multiple planets instead? This is very naive, so you will have to excuse me.
One of the beautiful things about the last few missions, Kepler and Webb, is that we have actually detected multiple transiting planets. So two planets transiting at the same time. And what is beautiful about not getting confused is that the positions of these planets obey Kepler's law. It's non-Keplerian dynamics because it's not a two-body problem, but it's gravity. Gravity is easy, right? Gravity is easy. So we know very well the timing, the so-called ephemeris of the planets. There's no confusion behind that. And in fact, there's a whole industry of astronomers who spend their careers just measuring the positions of these planets, just to make sure we're not confused.
Thank you.
Yeah, I would like to continue this discussion, and I also have questions, but we need to move on and go to the... Welcome to the second part of this morning session, and we are now more directly looking at the Earth and some of its most relevant and, for some respects, most dangerous processes. So the first talk will be by Professor Arnau Folch. Professor Folch is based in Barcelona at the Research Council of Spain. He's an expert in optimization on numerical codes, and especially for what concerns complex space-time codes of geophysical processes. He's the coordinator of CHEES, the Euro HPC Center of Excellence for Exascale Computation, and he's also part of the board of the Destination Earth initiative under the Digital Europe program, of which he's gonna tell us today. So please.
Okay, thank you very much for the introduction and for giving me the opportunity to present you Destination Earth in particular and talk a little bit about digital twins in general. No? So this is the outline for my talk today. I have separated in three different parts. First, some general slides about the concept of digital twin and the implications, because I think that there are many misunderstandings regarding digital twins that I would like to clarify. Then I will spend most of my talk talking about the Destination Earth initiative. And then at the end, I will talk about a project that is preparing the next generation of digital twins that will be integrated in Destination Earth. And in particular, one digital twin for geophysical extremes. So that's the question, no? What is a digital twin? I did the experiment to ask this question to some colleagues, and you might get really very different answers, no? You might get answers like, for example, well, a digital twin is a virtual replica of an object. This is true, but it's not the only true, it's just a part of the story. You might get answers like, well, a digital twin is a fancy modern concept to name what we actually have been doing for decades. That's modeling. That's a tough one, eh? Yes and no, it's actually much more than that. Or some people might tell you something like, well, a digital twin is just a data-driven modeling. So actually, which is the difference between a digital twin and the traditional data simulation that we have been doing for decades? Okay, it's true that digital twins are data-informed systems, but we will see the difference between both, okay? I got another funny answer. A digital twin is yet another niche for boosting artificial intelligence. Well, yes and no, it's not necessary. It's true, and we will see why digital twins are very coupled and very suitable for AI algorithms. But they are not necessarily, they do not necessarily go together. You might run a digital twin without any AI component, let's say, okay? So having said this, let's see two important concepts. The first one is the concept of digital replica. Actually, this idea is not new. It was born during the Apollo Moon program at NASA, and at that time, the engineers of NASA were developing a one-to-one replicas, a one-to-one scale of the service models. And they did that in order to evaluate possible solutions if some unexpected problem occurred during the missions, right? In fact, during the Apollo 13 mission, that was in April 1970, they had an accident. That's the famous oxygen tank explosion, no? That gave, in which the Houston, we've had a problem sentence was pronounced, no? And these analogical twins at that time were really fundamental, were really key to help engineers on the ground to solve the problem with the replica and then transfer the results to the spacecraft and to succeed with the rescue of the mission. No, actually, the Apollo 13 did not land on the moon, but came back to the Earth safely. Okay, that was in the 70s, and the concept of digital twin came 3 decades later, in the early 2000s, and was coined by Michael Griffiths from the Michigan Tech University in the context of the product life cycle management. And this allows me to introduce the very second important concept, which is the concept of life cycle. And I want to do here an analogy with what in software engineering is called the DevOps cycle. What is DevOps? DevOps is a methodology that software engineers use during development of projects, and it consists on a two-phase iterative methodology in which first they develop, and develop includes planning, coding, so that's writing a code, testing, building, and so on, and a second phase which is operations, in which they release the code, they deploy the code, they operate the code, and very important, they monitor the code, okay? And why they monitor the code? They monitor the code in order to offer feedback. So that's to close the life cycle of the software development, okay? So this is the develop. That consists on these 8 steps that you may see here. So if we put all together, we can answer now, or we could come out with a more precise definition of what a digital twin is, okay? So this is my personal definition. So a digital twin is a virtual life cycle environment which has to have 3 ingredients, okay? First, it has to have some data-informed replica of a real system or a real object. Second ingredient, it has to have some model-based prediction capabilities. So that means, in our slang, in our wording, the capacity to produce or to simulate many different scenarios, to contemplate many different scenarios. And the third ingredient is that it has to have the capability to provide feedback. That's to close the life cycle loop and to modify to close the loop and to modify the real system with this feedback, okay? Well, this is a quite strong and strict definition that works very well in an engineering environment in general. But if we want to be more inclusive and try to accommodate other communities, that's a bit more complicated. We may have problems, for example, with system accessibility, or we might have problems with the time scales of this life cycle. No? Consider, for example, the case of climate change. Okay, we have a twin for modeling climate change. We monitor the Earth. We have a digital replica, a very nice replica of the Earth. We have very complex models to simulate what may happen if I reduce my emissions by a 10%, by a 5%, by whatever. I have many scenarios on that. Then I go to the politicians. They make decisions, we apply these decisions, and then we have to wait to close the cycle and to start again. And of course, you may see that this may take years or even decades, no? To analyze what, if the decisions that we are taking today were adequate, were good or not. We can have even more extreme cases. For example, if we have a digital twin of the universe, in which we map the universe and we do a hypothesis about, I don't know, I'm not a cosmologist, forgive me the cosmologist, but about the amount of dark matter that there is in the universe, if it's a 5%, a 10%, a 50%, whatever, and based on that we decide whether the universe will behave this way or that other way. that's fine, but it's obvious that our capacity to modify the system is 0, no? So it doesn't fit in the strict definition of a digital twin. So this is why we could adopt this more weak or relaxed definition to accommodate a wide range of systems, which is essentially the same, but in the third component, we say that ideally, if we can, we have to provide feedback to the original system, okay? If we put everything in one single plot, I think that is a very nice and very remarkable analogy between the DevOps software cycle that I introduced before and the digital twin. Actually, they match super well, no? For the digital twin, we have also similar steps. So we have an initial step in which we collect data that can be historical or from data streams, so it can be real-time data or it can be historical data. Then we have a third step in which we analyze the data. Essentially, we pass quality control checks, etc. We work a little bit with the data. We do some kind of pre-processing step of the data in order to reach the fourth step in which we already have the replica. So we have built the replica. That's a data-driven picture. Or if you want a film, if we have historical records, it doesn't have to be a precise picture of the present. It can also have an historical component, so go back in time. And then, okay, we are done. We have the first part of it. We have the digital replica, but that's only the first part of the story. Then we go into the future, and we enter into what it's called the what-if scenarios, which is very analogous to the ops phase of the DevOps cycle, okay? And here what we do, okay, we run a scenario, so we can run models. Models understood in a very broad sense. It can be physical-based model, or it can be AI-based model. It doesn't matter. We run some kind of models to make predictions about the future. And then we visualize the impacts, which will be the consequences of these multiple scenarios that I'm considering at the same time. And then we make decisions. Well, probably we know, because the step number 8 is something that very often goes outside, or is something that is beyond the scientific scope, no? It's some decision maker that have to adopt decisions based on that, and then take actions. Close the loop and start again this kind of ideally endless replica what-if scenarios analogous to the DevOps cycle, okay? In terms of components, we have here the observations, which is something that we collect and that we typically store in a data lake. The term data lake suggests that we have rivers of data flowing into a lake, so that's the idea of this name. We have observations, then we run model in the second phase. We feedback the data lake with predictions, so a data lake actually contains both. It contains the data streams or the data, the replica, and contains the predictions. And then, very important, we have an arrow going down to the reality. That's the arrow that closes the life cycle management loop, okay? Which is quite important. So applications of digital twins. Nowadays, a lot. We have a myriad of cases where we can apply this philosophy of life cycle management, no? Of course, the original one, manufacturing, for mirroring all the design life cycles. This is why it was born, the concept of digital twin. But nowadays they are applied in health, personalized medicine. For example, we can have a twin, or ideally we will have in some years twins of human bodies, of your human body, not of a human body in general, of your human body. In automotion, for designing and improving performance, urban planning, wind energy, management of wind farms, etc. Okay? In detectors, in astrophysics, high energy physics, a lot of applications. They are ubiquitous, almost everywhere, the concept of digital twin. And of course, inner science systems. This is where I will focus my talk today, no? I'm sorry. Okay, so why these digital twins are boosting, or in other words, why I'm giving you this talk today here, no? This is not, it has not a single answer to these questions. Actually, there is a confluence of different factors, but I think that two are very relevant. One is the boosting and the ever-growing of HPC, of computational capability. We have entered already the exascale era. That means that we have computers, supercomputers, that can perform one exaflop. One exaflop is 10 to the 18th floating point operation per second. In Europe, for example, since a few years ago, we have in place the Euro-HPC joint undertaking that is deploying several tier 0 and tier 1 supercomputing systems. We already have 2 pre-exascale. That pre-exascale means that supercomputers able to perform more than 100 petaflops per second. So that's 0.1 exascale flops per second. We have 2. We have Lumi in Finland, and then we have Leonardo in Italy, at Cineca. Mare Nostrum 5 in Barcelona, in Spain, it will be deployed very soon, okay? And then we have another range of second class or lower class systems, a lot. We have Euro-HPC has deployed 5 of them in the last 2 years in different European countries. What I'm showing this is to show that we have already everywhere in the world, but in particular in Europe, a tremendous amount of computational capacity. And Euro-HPC has signed an agreement, is committed to give 10% of the computing time of all these systems to the Destination Earth initiative. That's something that we haven't, it's a dream for us, for the people that have been working on modeling this kind of things. Believe me, it's really a dream come true. The second component is the high-performance data analytics and the IoT, the Internet of Things. I don't think I don't have to talk about this, it's obvious, no? But with IoT, actually, the digital twins are becoming cost-effective, and we have now the capacity to collect, digest, process, whatever, inject into the models large amount of data streams of real-time data coming from sensors, okay? And of course, the answer to the first question, yes, this is the beautiful scenario for AI modeling. This is where they live. They love that, okay? Particularly if we use machine learning, it's the perfect playground for digital twins, even if the 2 concepts are different. We can run a twin with physics-based model. That's not a problem at all. But the scenario is really suitable for employing AI-based or machine learning-based modeling, okay? So with this introduction, I go now to the Destination Earth, and I will do a kind of recognition, go back in time, how this initiative was born. Actually, the origins of Destination Earth are in a proposal that was submitted some years ago that failed. That proposal was named Stream Earth and was a proposal coordinated by the ACMWF. ACMWF is the European Center for Medium Weather Range Forecast that was submitted to a FED flagship program, okay? And I put a sentence on which was the main objective of this proposal, that was to develop technologies for a required 1,000-fold increase in computation and fundamentally redesign workflows for a new generation of model and data to users. This is the essence of Destination Earth, okay? As I said, this proposal failed, did not pass, but to some extent it was a kind of phoenix birth, because it was an embryo for the Destination Earth initiative. And what is Destination Earth? Well, Destination Earth is a major initiative, actually it's a flagship initiative from the European Commission that aligns with the European Green Deal, with the European data strategy, with shaping Europe's digital future, okay? 3 main objectives. First, to develop digital twins for the Earth to monitor and predict all the environmental changes and the human impacts. And we want to do that with evidence-based policy developments, okay? And with actionable predictions. That is, it has to have a downstream component. This is the one that closes the replica what-if loops, okay? So it's not something closed, it's something that will require, once in place, the inputs and the participation of the whole community, okay? This is a very important point. It has like 3 main ingredients. 1 data lake, 1 digital twin engine that will run the twins, and then what is called the Destination Earth Core Service Platform. That's the entry portal. I will describe all these components in detail. And in terms of funding, most of the funding comes from the DG Connect. DG Connect is the Directorate General for Communication Networks, Content and Technology, which is funding the first phase, which is a tender, okay? It's a kind of procurement to 3 different entities to implement the first phases of Destination Earth. But then it also comes with substantial funding for additional air research and development activities from Horizon Europe. So that's the 3 pillars of Destination Earth. First, we have I will start from the bottom, from the digital twin engines. This is implemented by ACMWF, and it consists essentially on simulators that run on these extreme scale HPC systems. The objective, okay, provide users with initially only climate and weather information at scales where the impacts take place, okay? Then there will be the data lake in which the user will be able to find, discover, work with this data that the twins will flow, the results from the twin will flow into this data lake, and the user will have also some big data processing services on site. And this is a relevant thing. I will talk about this later, why it's important to work on site and not remotely. And finally, we will have the core service platform. That's the entry point for the end users, okay? And this will be a kind of cloud-based front end that will give the opportunity to end users to develop downstream services, okay? Downstream services for doing the simulations of these what-if scenarios and taking all the decision-making options. In terms of production, it's good to distinguish between two different production modes. There will be what is called a kind of more continuous mode. That's the generation of data from the twins, the replica. That's the generation of the replica that will go into the data lake, okay? And this is the one that will benefit from this 10% of computing time that I was mentioning before. So that will run in a continuous mode, for example, for the weather. So that will run daily weather forecasts at very high resolution, at a resolution that we have not been able to achieve yet, okay? So that's the continuous component. And then we have what is called the on-demand components. That's on the user side. That's, let's say, outside all this continuous mode, in which will be user-driven, and the user will use this on-demand mode through the Destination Earth service portal. To do what? Okay, to do, for example, more localized, focusing on one particular region, because Destination Earth has a global ambition, but then I want to put the focus on a particular case, or use the data in the data lake to add on top of that my own model, running my own simulations with my own model, feeding from the data generated by the twins, etc. So that will be on demand, and it's cloud-based. There is also the discussion about what we call the event-driven, no? Okay, we have this twin in place, but what happens if we have an earthquake right now, or a volcanic eruption, or we have some extreme phenomena, okay? Then we need to have some kind of urgent mode access to these computational capabilities and run in a kind of urgent mode. So this is something that is still under discussion, how it will happen, but I'm pretty sure that it will happen. During this first implementation phase, there will be two twins initially, okay? The first one is on weather-induced extremes. So that's what is called the extremes digital twin, and it will have two production modes. The first one is the continuous production mode that is implemented by ACMWF, it's a terrible acronym, in which the idea here is to run the IFS model, okay, at global simulations at 4.5 and almost 2.8 kilometers grid space resolution, okay, for a 5 days horizon. This is a lot. Just to give you very rough numbers, no? Imagine that we have a data cube in which we have this resolution. We are modeling the Earth at 3 kilometers resolution. So more or less in longitude, we have of the order of 10 to the 4th grid points. The same in latitude. Along the vertical, in the Z direction, in height, we may have 10 to the 2, 10 to the 3 probably grid points. Number of output time steps of the order of 10 to the 4. We store it in 4 bytes. Work out the numbers, and it gives you that at least order of magnitude. For each variable, it is like 10 terabytes, okay? Daily, for each variable. These kind of models are generating tens of variables per day. So that means that we are generating, or this will generate something probably close to almost 1 petabyte of data daily, okay? This is huge. And I want you to think about the change of paradigm that it implies, because the users of supercomputers have been always working in a model-centric paradigm in which we have our data outside the computer and the model in the computer. And we bring the data into the model, we run the model in the computer, and then we take out the data and we bring it back. This is not possible yet. I cannot start moving petabytes and petabytes of data with the current grids that we have. That's impossible. So we are shifting towards a data-centric paradigm. I have to bring the model into the data because the data is so big that it cannot move. It has to be there. It cannot be moved, okay? So I have to bring the model into the computer, compute, post-process, do some kind of rescaling, regridding, make it lighter, and then take the results. And this is why they have to develop this service portal, because the data will be there. You will have to bring your own model into the computer, run there, and then get the results back, okay? That's for the continuous production mode. But then there will be this on-demand production mode in which the user will be able to set up and to downscale in some particular regions of interest or for some particular problems of interest. For example, for studying wind farm, so that's more associated to renewable energy, flooding, using other models. For example, there is one use case in place which is based on the EHIVE model. Study air quality with the models that the community uses. So this is not forcing the communities to change what they do daily. You will be able to bring your own model, but that's the only thing you have to do. You will have to bring your own model there, probably in a containerized version of the model, because the data is so big that you cannot move it. Run the model there, and then take it back, okay? So that's for the first twin. For the second one, there is a second twin on climate change adaptation. That's what is called the climate adaptation DT, also with one continuous production mode and one on-demand production mode. And here they will run the ICON model and the IFS model coupled with the NEMO and the FISO model. So essentially these are models for the ocean, atmosphere, and ice sheet all coupled together, okay? To run multi-decadal, so that's predictions of the climate 10 or more years ahead at 5-kilometer resolution for different climate scenarios. So what might happen depending on the emissions, depending on multiple scenarios. So they have tens, hundreds of scenarios to contemplate heat. This is also a huge data cube, believe me, huge data cube, okay? That will be there, and then there will be the on-demand production mode, more or less analogous to the other one, no? So that's the roadmap for the destination. In the first phase, they are running, or they are preparing two twins, and they will, in the second phase, extend it to more applications. But at the same time, in parallel, there are several projects in Europe running under different calls, in particular under one infra call and and another call for doing other twins that potentially can be integrated in a near future into destination Earth, okay? And this includes DTGeo, which is a digital twin on geophysical extremes. This includes BioDT, which is a DT on biodiversity. This includes intertwin, and this includes a digital twin for the ocean. So these are candidates. And now I will very quickly, just a couple of slides about Destination Earth, which is this project that is preparing another twin for its future integration in Destination Earth, because I forgot to mention that one of the main objectives of Destination Earth is having all the twins coupled, working together. So it's not that we have one twin for the atmosphere, one twin for the extremes. No, no. The twins will be coupled because the Earth system is one single coupled system, and what happens in one component influences what happens on the other components. So we have this project that will deploy this prototype for digital twin on geophysical extremes, and that will develop digital twin components for different geophysical phenomena related to seismology, volcanology, tsunamis, etc. And we will do that by conducting data-informing early warning systems, probabilistic hazard assessment, and forecast, okay? It is important also the point of verifications, because all these components that are under development, under the umbrella of DTGeo, will be tested at what we call site demonstrations of particular relevance. So I skip that. This is just to show that DTGeo is not an isolated project. Actually, it's a kind of, is in an ecosystem of projects that work together in geosciences and HPC. And we have a very nice landscape nowadays in Europe of projects that are in synergy and that benefit one from the other. So that the outputs of one project serve actually to build many of the components of the other projects. This is just to show you the complexity of the ecosystem that we have today in Europe. These are just a list of the different twin components, and we will focus on modeling some aspects of volcanic phenomena, like atmospheric dispersal of volcanic clouds, modeling of lava flows, modeling of gas dispersal, etc. Also for tsunamis, as I mentioned, and then for earthquakes across different time and spatial scales. That's just to show you the different site demonstrations that cover many areas of Europe, but not only, because we also have applications of this digital twin in other places like Japan or Chile, for example. And that's essentially it. This is quite technical, okay, but it is just to show you a mapping of architectures, the architecture that we have in DTJ on the right and the architecture of Destination Earth on the left. What's the situation today is that we are developing independently, in theory, many different twins. And the question, obvious question, okay, how they will be coupled in the future if everybody has its own roadmap and adopts different solutions. And the thing is that we are coordinating the different initiatives in order to have at least compatible architecture. So there has to be a mapping, the particular solutions that you adopt, the particular software scheme, whatever, the different components for deploying your workflows, for running, for metadata schemes, whatever, can be different, but at least there has to be a mapping and we have to develop the interfaces. So it's that the different, I'm talking now at a level of very basic architecture, the different twin components have to be able to talk. And I leave it that with that future perspective. For more information about DTGO, you can always follow us on the different media. Okay? Thank you for your attention.
We already have one question there.
So this is half a comment and half a question. I keep wondering about, we are in this age where we're starting to see a difference between information and knowledge, right? Because I'm wondering, for example, if you're very conservative and you run a simulation, you produce correlations. You don't produce an explanation. To turn your correlation into an explanation, you need physical understanding. So to give the example of your Earth example, despite 50 years of research, physicists don't have a complete theory of turbulence, which means that they cannot give you a physical explanation for the boundary layer between the atmosphere and the surface of the Earth, and we cannot give you a physical theory for turbulent moist convection for forming clouds, which is important for climate change, as you know better than me. So my impression is that one cannot solve these problems by buying a bigger computer. And then here comes the question, which is, I imagine that there are some problems like self-driving cars where I don't care. I have lots of data, I predict, and I don't care about understanding. And then there are some physical systems where I don't get very far by buying a bigger computer, but maybe you're happy with that. Maybe you're happy with prediction with incomplete understanding. Can you comment?
Sure. I fully agree with you. I mean, basic research has to be there. This is not incompatible with doing basic research in parallel. This is the first point. I don't understand exactly your concern in the sense that this is just a high technological tool that allows you to do things. But of course, as you said, garbage in, garbage out. So in parallel, of course, you have to be developing your physical theories, your explanations for what you observe, for whatever. But I mean, I don't see that this excludes, that one excludes the other, no? It's obvious that we have to do in parallel basic research at many levels. This is obvious, yes.
Yeah, I may add that this kind of tools here are the same that have been used and continue to be used heavily by the scientific community in order to understand the physical aspects of the processes they deal with. So it's not just producing something, it's also exploring something before producing. Yeah, it's clearly, yeah. There is a second question there, and then.
Yeah, similar to the previous question, just a very practical question. In terms of climate and atmospheric and ocean circulation, models exist. I mean, like as a climate model intercomparison project, which consists of a variety of models. IPCC is using them. Do you implement those models in the digital twins? And if so, how do you choose which model to take? You can't run like 5 simultaneously. And another question is, if you want to model plate rupture, you need a geodynamic model that models lithospheric strain and so on. Does this even exist, and what do you use to do that?
Okay, we'll start with the second one. In terms of geodynamics, there is not in perspective any one, although I fully agree that it should be there. But at present, Destination Earth is more oriented towards a decision-making tool. No? It's more oriented to, or at least in this initial phase, give priority to phenomena that in the short term will give some kind of impact or will produce some kind of impact. No? So I'm not saying geodynamics is not at the base of it, I'm not saying that, but it operates on another time scale. So they prefer to start with modeling whatever, a tsunami, a volcanic eruption, an earthquake, and then, of course, in the future, the idea is to have all the Earth system. But I just want to make clear that we have a problem of time scales here, and in the Earth system we have many different time scales, so we are starting with something that is more on a human time scale to make decisions.
There is a question there, and then there will be another one there. Okay, that's the order. So, there, please.
Thank you for the interesting talk. I noticed in the 12, in the list of the 12 twins, the absence of two important elements. One about glaciers, which finally will produce the absence at some point of water for hydrology. And the second has to be with the oceans, which are, in terms of far-field processes like the disappearance of ice in Antarctica, finally will influence the oceanic currents. So I wonder if these two elements will be part of this list at some point.
Again, the question is, the funding is limited, the time is limited, and we have to start with something. That's the only answer I can give, no? Of course, there are many things that are left out. This is obvious, I mean, but we have to start with something and be pragmatic, no? This is for DTGeo. I'm not saying that what you're saying cannot be incorporated in the future. Actually, we are starting, or one of the ideas to couple the tsunami models with the ocean model, of course, with the ocean twin with the tsunami model in one will be soon coupled. But we have to go step by step. This is a long-term endeavor, 1 decade ahead. And we have to start with something. We cannot start with the whole thing because that breaks our mind, okay?
One last question.
Yes, thanks a lot. I have also some doubts about the whole sort of the grand scheme. I tell you what, I would like you to have your comments. So I'm also worried about the physical understanding that was mentioned before, but I'm more worried at this stage about closing the cycle of the digital twin, because it seems this is a very complex and sophisticated, system of, you know, like Russian dolls of models that you can use in a customized way. And I understand they produce enormous information and very useful one. But the closure of the cycle into the decision making, I think it's very naive to believe that knowledge leads to political decision. I mean, we have infinite examples of this. For, you know, talk about earthquakes. You know, people know about L'Aquila since hundreds of years, but you know, the implementation of the right kind of construction was not necessarily perfect, and so many other cases. How do you ensure or improve the ability of the European community and the national governments, that's a different question, to take this into account and not just shrug it off, which happens all the time, as in the case of climate, as we all know.
Wow,
this is to me key. Otherwise, it's not digital twin.
We need 2
Otherwise,
years
it's
or
a model.
3 to talk about that.
Wish I can answer.
Sorry, I'm just saying that we need 2 or 3 years at least to talk about that. I fully agree with many of your concerns and points. They are obvious, no? But this is intended to be a tool at the disposal of the community. There is this critical thing of closing the loop. This is why I mentioned that this is a weak definition of digital twin. It's not a strong definition, because this is, I have to state this and make very clear, okay? But then at some point, we are not decision makers. I mean, even if some of the people in this room has been involved in emergencies and in natural hazards, I know what you talk about. But at some point, this is a tool that we, or the community, you can use for research, you can use for doing science, or you can use it as another tool for decision makers. I'm not saying that this has to be the tool in which they will take, the only one in which they will base their decision. I'm not saying that. This is just a high sophisticated tool with the best that we have in science right now. That's it. Now, whether it's good, it will fit their purpose or not, this is something that is beyond destination Earth. This is
okay. The discussion is really very, very interesting, but we have to move on, definitely. And yeah. By introducing the fifth and last but not least speaker of this morning session, Professor Jan Lavallée from the Ludwig Maximilian University, Munich. Professor Jan Lavallée is Canadian as an origin. He's been studying Canada, in the US, then in Munich, from Munich, then he got a position of professor in Liverpool, and then he came back to Munich, where he's a chair of magmatic processes and volcanology. I guess so, yeah. He is the recipient of 2 ERC grants, is arguably the most brilliant experimental volcanologist of his generation, and is one of the initiators of the KMT initiative, of which he's going to tell us today. So please.
Thank you. Servus everyone, as we say in Bavaria. Thanks for the introduction, Paolo. Today I will not actually speak about what I do on a daily basis. I'm an experimentalist. I like to take rocks in the field. I go to volcanoes, take these rocks, put them in an oven, heat them up, I squish them, I twist them, blow them up, I throw them at stuff, but that's not what we're going to see today, okay? Yeah, okay. But we're going to talk about the playground I like, which is volcanoes and magma. Okay. We're only ever going to have one Earth, but we need 5. So we need to understand it now. Right. We need far more resources than we have available at the present. So it may be that in the future we have to colonize and exploit the solar system, but for now we need to turn to better solution here. And obviously during COVID, we all had a bit of time to reflect on the world, what happened, and I think everyone knows the times they're changing, right? Certainly the climates are. It's in the news now, again. Some of us will remember in the late 80s and in the 90s, it was in the news. And then there was the Kyoto Protocol as well, and then that failed. And then one of the key reasons why that failed is the Pinatubo eruption. That simple eruption was able to disturb the atmosphere, the temperature, the CO2 emission, and all of a sudden, the media and the government could turn around and just say, look, it's not as bad as we thought. And that was a big reason why the Kyoto Protocol failed. So we need to adapt better solution. We need to increase our resilience to hazards. We need to find more energy, and we need to think about this climate problem. So this is a sketch here from the Leopoldino report, I believe from last year, that shows the relationship between the different spheres in the Earth. And on the left side, what I find amazing here is just by volume and by space, you can see how most of our efforts and thoughts have been about the atmosphere, the biosphere, and the hydrosphere, because this is where we feel the most of the impact on climate. But all of those are affected by what's below the lithosphere. And in the lithosphere, what you see here is, you can see water, CO2 coming out, in and out. And you see the word melt. Melt is there, written in small. And that's our magma. And that's where volcanoes come in here. So it's important because even though there's CO2 in the atmosphere, and that's what we're tracking, most of the CO2 or most of the carbon is actually on the ground. So there's a huge source there, and we need to understand how mass and heat is transported through the lithosphere. And that happens through magmatism primarily. So magmatism is important. Essentially, it is one of the key processes by which the Earth is evolved and differentiated. So the dense stuff sinks in the middle, forms the core, and the lighter stuff come to the Earth's surface and erupt, forming the atmosphere and the hydrosphere. So in that process here, volcanoes, they're the gateway between the spheres, right? They spew out a ton of ash, a ton of gases, primarily water, sulfur, and carbon dioxide, but they also release the entire periodic table with it in the process. When you look at the budget of gas coming out, primarily it's water. So water is the problem in the Earth system. Water wants to come out, and it drags with it some molten rock, and it creates the volcanic problem. Recently, with the advances that we have from satellite-based sensors, we have a good idea of how much gases essentially is emitted at volcanoes, and we start having fluxes. Here we see sulfur dioxide or carbon dioxide in these cases. These data are really new. We did not have this even 5 years ago. It's only the last few years where people have started compiling all of this information around the world. And that's important because volcanoes, when they erupt, again, they release a lot of material, and that material gets transported in the atmosphere. And here we have the case of El Chichon in 1982, and you can see that the volcanic plume took about 20 days to go around the world. It was close to the tropics. 20 days it's what it takes. And you can see on the right-hand side that ash plume, gas and ash plume, changed the radiance on Earth. Okay, so volcanic eruption, they have the potential of heating, resulting in net heating of the atmosphere and some time of cooling. And it depends on the types of eruption that take place. So we start having better budget of volatiles coming out of volcanoes. That's a good thing, but that's what we measure. And here's just a quick slide, some experiments that were done in Munich here before my time in the group of Don, which shows just how quickly the sulfur dioxide from the eruption can react onto the volcanic ash. In a matter of a few minutes, you can sequestrate or uptake 40% of the sulfur that precipitates on the ash. So somehow, these processes, they've just been newly discovered. We need to start putting focus and efforts on those to try to understand what really happens during a volcanic eruption. So our budgets, they need revisiting. We just start having them, but we start seeing issues already with them. Each volcano is a bit different than the next, and as a result, the gas that comes out of them is also different. But again, having our budget recently established, now we can start seeing that active volcanoes, dormant volcanoes, they don't release the same gases and in the same proportion. So we can gain information about the state of the magma below the volcano. And that's really key here, because ultimately, this is where the source of the issue is. So slowly, I'm going to try to make my way towards magma and what they are. There's 3 ingredients to magma. The most important is a melt. There's a melt phase, it's molten liquid, molten rock. And then we have variable amount of crystals and bubbles of exalt volatiles, essentially. And those 3 ingredients, well, they're dictated by the pressure and the temperature in the Earth. And as magma are transported through the Earth, their conditions evolve and they start crystallizing, they vesiculate, and it changes their properties, their viscosity, their density, and so on. And that affects whether the magma will make it to the surface and erupt or get stuck in the crust. In volcanology, we're full of these cartoons. They're really nice, but the reality is that they're just cartoons. We don't really know where magma is below the surface. We can go to old solidified magma reservoir that have sort of crystallized and then have been eroded, and we can look at their architecture, what the magma rock interaction might have been and so on, but they're just models. We don't know what magma look like underground. We cannot detect them or image them at the present, and that is a major drawback that we have. So, what we have is more cartoons. That cartoon is not better or worse than the last one. It just shows different aspect here. There's a magma, and that magma is trying to make it to the surface. It shows there's a hazard at the Earth's surface. There could be ash, there could be gas, could affect aviation, could affect us. But importantly, on the ground, there's this mass movement around the magma as well. There's a lot of fluids, and those fluids, well, they're hot. They cause geothermal system. We can exploit them. They also deposit all of the ores, lithium as well, and so on. So there's a lot of need to understand what happens at this magma rock interface. Obviously, the volcanic problem is known. We've all had to deal with this through time. There's an example here of Pompeii or this eruption in Chile. So volcanic eruptions have wiped out towns, cities, and civilization. They can be a problem on a daily basis. And if we want to better forecast what can happen, well, we need better data. That's the whole point of the discussion today. In general, we can tell relatively well when something might happen, but we can't tell how it's going to happen and for how long. Is it going to be a one-day event, or is it going to last 100 years? And we have no idea when things start, when they're going to end. So we need better data. So we need to understand the volcanic hazard, especially considering that there is close to 1 billion people living within 100 kilometers of a volcano. But that also means that all of these places are sitting on magma, and they're also sitting on a ton of energy. And how big are those magma? Well, we can turn to volcanic eruption for that. We have small eruption, as we see here from Mount St. Helens in 1980. And that very small eruption, which caused a huge plumes, was only 0.1 cubic kilometer. And you can see at the other side of the scale that some eruptions in the past have been as large as a few thousand cubic kilometers. So there's a lot of magma underground at times. And these deposits from those larger eruptions, well, they can cover entire continents. And that's what remains some hundreds of thousands of years later. So how much was really erupted, we don't really know, but that's what we see. And I'll give you another example of this. I studied an eruption that was 11 cubic kilometers that took place in the year 1600 in Peru. And now we go back 400 years later, and we can't find the ash anywhere around. They've been carried out by wind, and they form sand dunes in the desert, some 300 or 400 kilometers away. The ashes just vanish and goes back to sea, essentially. So our data, we lack some of the information to really understand the scale of the problem that we have. And from our textbooks, this tells us the different ways we can get killed by volcanoes, and then what we do about it. There's a lot of volcanic hazards, from the gas erupted, the ash, pyroclastic flows and lava flows, and we understand those often relatively well. But as I said, we can't really forecast what will happen in the course of an eruption. And despite the best measurements we have, and we have a lot of measurements, and we have a lot of data in the last 3 or 4 decades coming out from different volcanoes around the world, one of the issues is that everything we use is at the Earth's surface, or from space, and we look at the Earth's surface. We're lacking the data in situ at the source of the problem. So these parameters are somewhat unknown. We need better data. And that is, there's a lot of effort toward getting better data. This is an example here of volcano monitoring in Italy, thanks to Paolo for the slide. They're getting increasingly sophisticated, yet we need better ways to move forward, especially if we want to better live with volcanoes. They provide resources. There's a lot of heat. They provide us with the raw material, and some countries have done better than others at this, right? You can look at Iceland, where until a few years ago, Iceland, the energy was essentially almost free in Iceland. It is very cheap because they produce so much of it through the geothermal. Most of it is used for heating space, but some of it is converted to electricity. And when you look in the past in Iceland, in fact, they save on average $1,600 per capita every year by using geothermal instead of burning oil to produce their energy. And some of it is for space heating, but it's also used for the industry. So just how much energy? And if there's one take-home message that I want you to have, is that cooling 1 liter of magma from 1,000 degrees to room temperature generates 1 megawatt. That's all you need to remember. Now try to extrapolate this to 2,000 cubic kilometer. There is a ton of energy. We need to find a way to access it safely. Okay? So magma, when they're cooling, they're crystallizing, and as a result, they're densifying. And when they densify, they crack, and they form these beautiful colonnades that we see around the world. The beauty of those colonnades is that as they form, they are pathways for fluid to ingress towards the magma and get back out. So they are the main source of heat exchange from the magma to the rock to our geothermal system. So the geothermal company, they realize that. They realize that they need to go deeper to the source of the problem. So they are already primarily interested in volcanic landscape because there's so much heat in the ground. It's just readily available to be utilized. But they want to get closer to magma. And then the issue with this is that you disturb the system. That's an example here of Puna in Hawaii. These are data that are recently obtained, and we need to try to model this here. In the year 2018, there was a 4-month eruption in Hawaii, and you can see here the lava flow on the left, and the color codes here shows the displacement. And in particular, it shows the displacement at the point where, 2 years after the eruption, the geothermal company said, well, we can put fluid down on the ground now, and we want to harness that energy. And then you see the contraction of the magma that's cooling, and the ground is subsiding related to that fluid injection. So clearly the magma, they respond to our activities. The question is it good or is it bad? And we don't know that yet. Certainly, we can get a lot of energy from it, but we need to find ways of manipulating the system in an understood way. There's another example of this, which took place in 2009 at Krafla volcano in northeast Iceland. There, despite some of the best geophysics at a volcano around the world, they thought the magma chamber was at about 5-kilometer depth. And then they started drilling. They wanted to go to 4.5 kilometers to get supercritical fluid, and then boom, at 2.1 kilometer, they hit a little body of magma. That's the third time that it happens by geothermal companies. They wanted the energy, so they went there. Luckily, nothing happened. Magma did go up the borehole by about 10 meters, and then it quenched itself, and it stopped flowing. And what they do know is that it produced a huge amount of energy. That's the hottest well in the world, and that produced about 10 times more energy than a conventional well in Iceland, which are already highly productive. The good thing for us is now we know where the magma is, finally. So here's what we can do with this. So here I'm going to go through a series of a few slides and showing you some of the challenges. Again, we did not know where the magma was. The energy production was associated with a lot of corrosion, so there's an engineering challenge here that needs to be overcome if we want to use that. Interestingly, when they were drilling, as they approached the magma, they have to use cooling fluids, and they lost all of those cooling fluids, which means that the rocks are extremely permeable. The fluids are able to flow around magma, and they did not predict that. In their mind, when the rocks get soft, you can't break them. But we know that magma breaks. We know this in volcanology because that's why we have explosive eruption. But in the geothermal business, they did not know that. And all of a sudden, we're coming along and we say, actually, this is the best place to fracture the rock. If you want to have fluid exchange, that's where you actually need to go. Not where you've been looking for the past 100 years. It's at the magma, it's at the source that the real stuff is. So there's a lot of opportunity that comes with this. As I mentioned, there's a lot of energy. We know that the fluids can flow in that area near the magma. But importantly, because now we know where the magma is, we can go back through our data and we can tweak the signal and see whether we can see that magma. And then, now that we know the answer, we can go back to the seismicity, for example, and yes, we can see that there might be a magma now, but we know now, we need to know the answer, essentially, to improve our models. So we need to do better on that front. And what that gave us is the first sample of quenched bits of magma from a magma chamber. So it means that those pieces of glass that were quenched, they did not erupt to the Earth's surface, they did not go through that process. We can just quench them in situ and we can try to understand what are the conditions for magma. Why was this magma happy there? Why did it erupt? Why they intersected it? Okay. And it also gave us an idea of the temperature gradient around the magma chamber. The temperature drops from about 900 degrees to about 400 degrees over the space of 15 meters. None of our models would have predicted that. For what we've assumed for a long time, we would have thought that it would have been a much slower gradient, but it's a very steep gradient. So again, that means that there's a lot of fluid exchange with the area to promote that. So in volcanology overall, we have a bunch of challenges we need to overcome. We need to understand the contribution of magmatism in the Earth system, And we need to quantify the state of the magmatic, the hydrothermal, and the volcanic system and their interaction. We need to do better at detecting magma reservoir and at monitoring the state of these magma in real time. And then we need to find a way of accessing those beasts in a safe way. And that's what we're planning next. We're planning to go back there, to drill back into magma, but plan for it this time and make sure that we have the right drilling strategy to create a world-class international magma research infrastructure. So we've been working at this. Don has been involved, Paolo has been involved here, and many more people around the world from a lot of institutions. We've been working at this for 8 or 9 years, and now we're facing the time where this might happen. It's a lot of effort, but we need to build this. At this stage, we are in the preparation phase, what we call our phase 0. So we need to think about governance, we need to bring money, we need to develop all of our engineering and science strategy, design the well, and so on. And what we're planning essentially is 2 wells in the magma to start with. The first well will consist of drilling through the rock magma interface, sample magma, and instrument magma. So that is going to become our observation well. Once we've done this, then we can start revising our models and then prepare for the next drilling phase, which will be to drill next to it and then conduct different experiments. We need to know, as we're drilling through the cross, at what point does the magma react to our drilling activities? We don't know this now. We know this magma was not primed to erupt in 2009. Hopefully it will not be this time either. But if we want to develop this technology and utilize it elsewhere around the world, there's a lot of things we need to understand if we want to develop guidelines to do this safely. So we have a huge series of activities that are planned to go and do just that. And we also have ideas for future, like using other wells, going below the magma and so on. We need to start improving the ways in which we detect the magma. What's their volume? What's the state? Could we don't only need to know, for example, the temperature every day. What's the pressure like? Is there new magma injection in this reservoir, or is magma seeping out through cracks and so on? So we see this as really the necessary step to modernize volcanology and bring volcanology and the geothermal communities together. So really we see this as a well of opportunity. Understanding magma is a better way to understand the Earth system as a whole, mass transfer, climate change, volcanic hazard, and energy. And I really think it's also a great way to connect the science together. In this project, we're considering how, we integrate everything with social science, hazard perception. For example, everyone will be thinking now, how will the public respond if you cause an eruption? Well, each country would see it very differently, right? We all hear about fracking. A lot of countries are worried about this. Well, in Iceland, their view was, eruption happen all the time here. It'll just be another one. So that's quite surprising, but it means they're very receptive to us trying it. Education, we're looking to develop like an education center, and certainly like communication to the public is going to be like central to that. Engineering is also a challenge. We need more extreme materials, more extreme sensors to do this. We don't need just this for drilling in magma, but also for our laboratories to essentially instrument the sample instead of instrumenting outside of a machine. Origin of life, space science and exploration, certainly the links are there. We heard great talks this morning, for example, pointing out at Kevin here in astrophysics, right? Understanding the evolution of exoplanets. Well, if we understand our own planet, then we can transfer that knowledge, so we need to work together and bring these activities together. And I really think that, for example, we discussed this topic of magma energy at Topo Europe, something that still started here as part of Academia Europaea some 20 years ago. And I think it would be a great vehicle to actually bring those communities together. So everyone's welcome. The problem is multidimensional. Thank you.
Thank you. Yeah, we are 2 minutes late, so we have time for 1-2 questions. Sirt. Wait for the microphone.
pre-existing faults. That was a great talk. Could you comment on the role of pre-existing faults and tectonic stresses on the dynamics and the siting of magma emplacement?
So yeah, so this is one of the main pathways for magma transport in the Earth is through fractures and faults. So we see that volcanoes around the world, in fact, if I go back here to an earlier slide, that is backward. Yeah, good. We have the distribution of volcanoes here, and you can see how, for example, when you look at the Andes in North America, you see this line of volcanoes here, and essentially that line is where the plates are subducting below the Earth's crust. But these rocks above, they're fractured. There's these very long fractures, and magma is coming through them, essentially. So magma has a tendency to erupt where there's intersection of fractures. And we see this there. We see this also when you look in the Alps. If you guys are, some of you are hiking through the Alps, when you go to the Southern Alps in Northern Italy, you see that there's all of these crystalline body of magma that crystallize along the faults there. So faults are extremely important, so it means we need to understand how the magma is impacting the state of stress in the rocks around, that there's seismicity related to that, and obviously the pathways for fluids in general. Very important.
Bernardo.
Thank you for the nice talk. As far as I understood, the site is in Iceland, right?
The drilling site is in Iceland, yeah. Yes.
And the magma is rhyolite, which is quite anomalous in a ocean ridge context. Yeah. Do the available data allow you to speculate on the origin of this rhyolite?
Yeah, within our KMT project, we have different views. So the question is it, there's a few things that are very interesting about this rhyolite, first of all, before I answer that. One of which is there's not many crystals in there. It's all melt. So it means that there has to be a lot of heat to keep this rhyolite, or let's call it granitic magma, sitting there without crystallizing. So perhaps there's underplating below. So it's very likely that it's a partial melt of the rocks around. And in which case, what it means for us in geology is that Iceland is meant to be a hotspot, but it created this really large island. And perhaps in understanding this magma, we could understand how the continental crust is forming. The continental crust has a very different chemistry than the rock we find at the bottom of the ocean. And Iceland might be one of the way of understanding that. When we look in the drilling, there's a transition just before that granitic magma. There is a crystalline equivalent of that. So some people have thought that maybe this is a partial melting of this. I don't believe so. I believe it's the other way around. I think it's the crystalline end of the melt. There's no, we can talk about long length about it, but there's no nanolite and a few things. But yeah, there's still a lot of questions, very basic questions that remain. And I think by drilling and properly coring through the interface and getting the sample across, we'll be able to resolve those questions.
Other questions? Okay, if not, we can declare concluded the morning session. Thanks to everybody. Thank you. And please reconvene here at 1 for the still exciting program of the humanity class. Okay, starting at 1 here. Thanks a lot.
Good afternoon. We are ready to for another exciting session. My name is Poul Holm. I'm the chair of the humanities class. And as you can hear, my voice has almost gone. It's not due to excessive carousing last night. It's just too much talking, I suppose. So I'll keep it brief, but I'm delighted to have the opportunity to introduce to you Professor Pascal Engel. Professor Engel is a world-renowned philosopher who works on the philosophy of language, philosophy of mind, epistemology and philosophy of logic. Engel has been professor at the universities of Caen and Sorbonne since 2006. He's professor at the University of Geneva. He has been president of the Société de Philosophie Analytique and editor of the journal Dialectica. He was elected to Academia Europaea in 2012. Out of his numerous publications, let me single out What's the Use of Truth, which he published with Richard Rorty. With Engel coming from French analytical philosophy and Rorty from American pragmatism, they presented radically different perspectives on truth and its correspondence to reality. It's a rare opportunity to experience the two sides of that debate so clearly and concisely. Among other recent works, Engel has discussed epistemology of belief and epistemic norms, intellectual ethics, and rationalism. His lecture today has the title, Truth and Normativity. The floor is yours, Professor Engel. Would you want to start?
Thank you, Professor Holm. I'm very delighted to speak at the Academia Europaea because I've always known the fact that I was elected, but I never spoke, so it's very nice to have this occasion. And thanks to the organizer and for the invitation, and to the technical team for the work they do on our very bad slides often. Before starting, I would like to give a little bit of contextual historical remarks about the topic I'm going to talk about. It's a topic which comes from the past of philosophy since the early days of philosophy, but the history of the topic is 2 centuries ago. It started when the field of ethics, and especially the series of values, started in the 19th century as a response to especially the British moralists and the utilitarians. In Germany, there is a debate which has been going on for quite a long time on so-called Geltung. And this was a topic which was a favorite of the Baden school, Heinrich Rickert, Windelband, Emil Lask, and such people who were debating about the nature of norms. And so at that time, the notion of value was competing with the notion of norm, and there was a large debate about the so-called normative sciences. Dilthey was also a member of this discussion. And this debate has more or less been withdrawn in the early 20th century, and then it was sort of swallowed by debates about pragmatism and truth and utility. And it has resurfaced recently in contemporary metaethics. And so this is a topic which is now at the crossing between ethics and epistemology. And there is a lot of work in that. And as someone trained in analytic philosophy, I am historically blind, but I rediscovered this history rather recently. So I want to talk about, I want to talk about truth and normativity, and also I must say that there is also another element of context which is directly contemporary. Someone recently said that the word normativity is a term which has been which is really too much present in the debates about the humanities and the social science. Everybody talks about normativity. And so it's a very, very wide topic. So these are very wide topics, much too wide and too big for someone who wants to talk for 25 minutes. So I want just to give a kind of sketch of the debates as they are, as they are operate these days, and it's going to be very much cubist at the moment where I would have preferred to be impressionist. So I will talk about the relationships between the two notions. I will introduce the notion of the truth norm for belief and examine two threads, relativists and pragmatists. And I will try to say a little bit why I believe that the knowledge norm for belief is better. And as a kind of upshot, I will talk a little bit about intellectual virtues. So the question that might be raised in the following way, is truth a norm? When I suggested that some years ago, one of my teachers said to me, this is completely crazy. I mean, why should truth be a norm? The norm of scientific inquiry is justify your theories. It's the fact that they are true is not such a big deal. I mean, of course we are aiming at it, but we want to justify them. So that's one debate. Another one of my colleagues from Cambridge, a place where you have a lot of commonsensical philosophers, said to me, norm is too big a term. You should say the standard. And I resisted for many years to this Cambridgian piece of common sense. So the question is, why believe the truth? And of course, the immediate or the directly contextually contemporary subtopics in this field, you know them. I mean, they are those of the relationship between science and policy, about academic freedom, ethic of knowledge, and indeed politics. And these days, of course, I think that many people would not like to have this subject raised in this sort of emphatic, or I would say bombastic style. Bombastic is the style of universities at the end of the 19th century. It's also not a surprise that people were talking about Geltung at that time, because you have mottos at the front of the universities, looking for the truth, science, and so on. And of course, this is not something which is in the atmosphere of today. When we say that truth is the norm or the goal or the supreme value of science, people tend to laugh. They tend to laugh because we have been sort of washed up by several generations of doubt about truth and of rejection of these bombastic ideals. But so many people are skeptical, and they say that there cannot be a norm of truth because there is no truth. That was one of the answers that Michel Foucault, when I listened to his talks a long time ago, was trying to convey. And of course, there is the relativist, or the pluralist, as they prefer to call them, camp. They say that there are many truths, and therefore many norms. So that's basically the kind of answers that you get. My own answer is emphatic and bombastic. I like the norm of truth, and even if it's rather old-fashioned to say so. There is a contrast between the two notions. Truth is very simple, but normativity is very complex. Why is truth simple? Because, as all philosophers have said, a thought is true, or a sentence or a proposition is true, if it corresponds to the facts. This is what Aristotle said when he said, to say what is true is true, and that what is the truth, and to say that what is not true when it is true is the false, and so on. And there doesn't seem to be very much more to say about it. And especially when you want to say that seawater is salty, that's true if and only if seawater is salty, as the common sense philosopher and the common sense want to say. So a belief that P, where P is any proposition, is true if and only if P. So that's what you have to say about truth. And especially it goes with assertions. To assert that P is true is just the same thing as to assert that P. And behind those trivialities are hiding a lot of bushes of complexities, but we can be happy with that at the moment. Now, on the other hand, normativity is very complex. I mean, it's an extremely plethoric notion. You have deontic normativity, oughts, must, permission, interdictions. You have axiology, values, good, bad, valuable, with all the vocabulary which goes with it. You have rules, you have laws, and you have reasons, according to a recent trend of people who say that the normative vocabulary should be the vocabulary of reasons. And in a more classical tone, as with the British empiricists, you have various kind of evaluative attitudes. So I'm not going to go into that. The main problem I want to address is the problem of the so-called normative force. Suppose that there is a norm. Suppose that you accept that there is a norm which regulates truth. The first question is, what is it? And if there is one, has it any kind of force? Does it move you? You may probably remember this cartoon, which I don't have on my slides, of Calvin and Hobbes. You remember Calvin and Hobbes. Calvin is going to have a bath, and he doesn't want. So he says, I don't care what's right. I will stand for my principles. And Mother comes, put Calvin in the bath, and he says, I stand firm to my principles, but they don't have the slightest impact on me. So this is the problem. A norm must motivate in some way. It must require and guide. And of course, norms do not guide in the same way, all of them. And it depends on the various domains of normativity. Deontic norms, when you use terms such as ought or forbidden, they are very strongly prescriptive, or at least it seems. They have a potentially universal scope. Values such as good, bad, admirable, or loathsome are less prescriptive. They are thicker, if you want, as people say. And they also can be relative. Rules and convention are prescriptive in domain-specific ways. Think, for instance, of rules of etiquette. I mean, they hold in certain sort of context, social, cultural, or epistemic. They don't have the same scope. And codes are contextually prescriptive, and all of these are very optional. So the question might be raised in this way. Does truth itself, do truth, such as true sentences, true theories, true propositions, have normative consequences? I mean, we have heard this morning and yesterday plenty of talks by our colleagues who gave us, I suppose, a lot of truth. But were you moved? Probably yes. No. Truths don't have normative consequences. The fact that seawater is salty doesn't entail in any way, if I think of the beliefs, that I ought to do or think or find it good or bad. It doesn't move me. Facts, the lesson is classical, do not entail values. And of course, this goes also for lies, ideologies, and post-truth phenomena. They are certainly worrisome, but they are not worrisome for truth itself. I mean, I've read a lot of books saying that truth is dead, that this is the end of truth, and so on and so forth. But that's not the end of truth. I mean, the fact that some people manipulate truth and do disinformation and propagate errors doesn't in any way change the truth itself. So this has been called the passus for fallacy, and we have been falling into this trap quite often. Sorry. But of course, the objection is, this is not the only thing. I mean, the important thing is that belief is the link between normativity and truth. In the sense which was proposed by this time, again, another British philosopher, G.E. Moore. He said, I cannot at any moment distinguish what is true from what I believe. Looks like the declaration of Billy Graham or such people of Adventist and Baptist preachers or popular politicians. This is not what Moore had in mind. He was not stating a sort of motto for dictators. He was just saying that when I think that something, when I say that something is true, it automatically is something which I believe. But what is the relationship between the two? We can formulate it, and I show it now, through a norm, the truth norm. You ought to believe what is true, and you ought to avoid believing what is false. Especially in two circumstances, which are called Moore's paradox. When you say, it's raining, but I don't believe it, this violates the first requirement. And when you say, I believe it's raining, but it's not, it violates the second requirement. But of course, when we deal with the relationship between belief and truth, is truth the only criterion? No. We often believe what is false, or we do not care whether what we believe in is true. We can trick people or ourselves in believing what is false. So the relationship is normative about evaluation of belief. It's not descriptive of belief formation. This is a mistake which is often done, especially by my colleague, I don't know whether he's here today, Jean-Pierre Changeux. He has written a book which is called The Physiology of Truth. And in that book, he says, truth is the brain. The brain is what explains truth and all sorts of mind phenomena. Okay, let's accept that our beliefs are brain-based, but that doesn't entail that the truth is itself a sort of brainy state. So the formation of belief, the formation of our beliefs is not normative, and we can see quite a lot of phenomena which are causal there. But it's not the same when we say that truth is a norm. Similarly, there are practical reasons to believe. There are reasons to believe that you are going to win the race. You are reasons to believe that you are a good conductor when you go into your Mercedes. But these do not seem to be the right reasons. I mean, in my case, I cannot at any moment believe that I will be able to drive such a beautiful car without wishful thinking. So these are not good reasons. So what is, again, the relationship? There is a triangle which is useful. It was proposed by Bernard Williams in his book, which is called Truth and Truthfulness. I think it's a very inspiring book. You have a triangle with the notion of truth, the notion of belief, and the notion of assertions. Belief have a certain sort of relationship to truth. Is it normative? It is a form of correspondence. It has relationship with assertion because you assert things that you believe. And assertion is a normal expression of beliefs, and it is the normal way in which we give this. So there is a nominal essence of truth, which is given by several marks, or truism about truth. The first one is the one which I have just mentioned, equivalence, the belief or the assertion that P is true if and only if P. There is another common sense thing, which is objectivity, a belief that true is true if only things stay they are. And there is a triviality about justification. Some beliefs can be true without being justified. Some beliefs can be justified without being true. And there is the norm of truth. So the proposal which I prefer, because I am like Heinrich Rickert, closer to the Kantians than to the Aristotelians in this debate, is the deontic proposal, which can be formulated as a correctness condition. A belief is correct if and only if it's true, or what ought to believe what is true, if and only if it's true. And of course, I do not ignore here, but I'm not going to talk very much about it, the idea that truth is also a value, maybe a supreme value. So in this case, you say it's good, valuable, or intrinsically valuable to believe that what is true and only what is true. But this norm of truth encounters several problems. The first one is that if we say that we ought to believe all truths and disbelieve all falsehoods, this looks very stupid, because we are not going to swallow all and to believe all the truths, including those which are trivial or which are impossible. And there are plenty of things that we ought to know and which is we ought not to know, which is not valuable to know. So could we say that typically the norm holds? But what norm is? What is a norm which holds typically? Of course, there are margins in the application of norms, but if you say it's a norm sometimes and not sometimes, just like saying that you are married just a little bit. So maybe we could think of weaker norms, such as evidence, that you ought to believe when there is enough evidence. But of course, the two norms clash. I mean, there are cases where you have justification or evidence, but you don't know the truth, and so you cannot apply this norm. And very often you have the norm of truth without having the evidence. And of course, if the norm of truth were always in application, it would be impossible to suspend judgment. And people have proposed that you are permitted to believe that P if and only if P is true, but of course it's too weak. I mean, permission cannot really give. So my proposal, which I have defended with many others, is that the so-called correctness condition on belief says that it is a commitment on belief. If you want, it's just something which says that it is fitting, or it is normally, in the sense of conceptually, the case that belief is directed to truth. And so this raises the problem that I mentioned, that is the motivation problem. Because if you know this norm, if you recognize it, how do you really apply it? That cannot move anyone. 5 minutes, okay? I'm not going to. So there is a threat, which is relativism. Relativism is going to say that there are as many norms as you want. And so this also sort of kills the notion of normativity. Well, one case which I like, and I just mentioned, where there is a conflict, is the so-called topic of epistemic injustice, where people kind of compare the advantages and the normativity of believing the truth and of satisfying the requirements of social justice. I'm not going to mention this solution. The second threat is a pragmatist threat, which is the worst, I believe. Epistemic assessments of beliefs are all the time, but which one is right? And I do not give many examples in this talk, but think of one topic which is very relevant about academic freedom and about the rule that we are all discussing always in universities. It says that the position in presence should be balanced. Very often, the rectors of our universities tell us that when there are positions which fall apart or are contradictory, they should be balanced. But the balance is a requirement of honesty, being nice, being respectful, but it is within the requirement of truth. It's not something which could, in some sense, sidestep or override the norm of truth. Similarly with the practical reasons for belief. Always they are trumped. Now, you can be a nihilist, and you can say, like Nietzsche, that truth is a woman, and you can imagine that people will believe one thing on the Monday and another thing on a Tuesday, but of course, would these people have really beliefs? So, I'm not going to discuss this. So, the question is, how can the norm of truth motivate? The norm of truth, just as a correctness condition for belief, doesn't motivate. And the norm of evidence is unlike the norm of truth, is not blind, but it's very subjective. You just see things from your point of view. So my proposal is the norm must be knowledge. The norm must be some sort of condition which implies truth, but which incorporates the requirement on evidence. Of course, 2 + 2 = 4, and truth plus evidence doesn't imply the norm of truth in the proper way, but that would be the solution. You ought to believe that P only if you know that P. You certainly ought not to believe what you know, but you ought to believe what you are in a position to know, which is, of course, difficult to guarantee, but it's how can you guarantee such a strong condition? Suggestion is that you should, if there is knowledge, have a sufficient range of counterfactual possibilities which gives to your knowledge some sort of safety. So the notion of knowledge, in the sense that it implies safety, has to be applied to the norm of truth. And of course, this leads you in some way, if you invoke the notion of disposition, to the notion of virtue, which was already there from the beginning. It was the notion of virtue which Aristotle discusses in Book Alpha of his Metaphysics. All men desire to know. So wanting to know has to be a certain sort of disposition. And you have to cultivate the disposition. So the disposition goes you back to the notion of value. I don't go into the debate on who is sitting on what. I mean, you remember the elephant which is sitting on the tortoise and so on. Are the values the tortoise, or is truth the elephant? I believe that actually there is the elephant and the tortoise at the same time, and they do not. But many philosophers believe that there is sort of foundational structures. Certainly, the big problem is that values do not prescribe. This is why I prefer the normative framework and the Kantian one, if you prefer. Because I cannot imagine at any moment that truth could be just kind of optional extra, or knowledge, according to my proposal. So I'm not going to talk about the norm of assertion, and I'm finished. The wider scheme that we need at this point is to add to the truth normativity framework the notion of intellectual virtues. But I don't propose to do it in the Aristotelian way. I prefer to do it in the Stoic way. Remember the Stoics. The Stoics had the same sort of framework as Aristotle, but for them, there were the duties, the norms in our language of today. And then there was the theory of virtues. So that's the way I prefer to think of it. These are the virtues of science: veracity, sincerity, exactness, accuracy. And I cannot think of a better scheme than the one which was suggested by the mathematician from Vienna, Carl Sigmund. You certainly know the book, Exact Thinking in Demented Times. Isn't it always the case? Thank you.
Thank you so much. This was a very rich talk, and I'm sure we look forward to hopefully seeing the full talk in the European Review in due course. But I'll give just one quick question, if there's one. Very short question and a short answer.
Yeah.
Louis.
Thank you very much. It was actually very, very interesting. My question goes in this direction. I think you pushed very well the arguments, also the risks and so on. But my question would be this. If in the end you relate truth to virtue, in a sense also to ethics and moral, and knowledge, in our society, wouldn't this mean that truth is beyond reach of most people? And if so, therefore useless in social terms? How can we actually convey a framework for truth that is not only addressed to single individuals? Could the intersubjectiveness be part of that? In a sense of probability as we use it in science?
Yes, very good. Well, of course, certainly we care much more for justification, evidence, data, and everything which is a way to access truth. And as I said, the norm of truth is blind. And if someone came to us and said to me, I am the truth, as one man did a long time ago, we wouldn't believe him, of course, because we don't know what truth is. But there is a problem, which is we know a number of truths. I mean, you certainly know what the amount, I don't know, because you said, I don't know whether you are a prudent man. Do you know the amount of money on your bank account at this very moment? You don't know, and sometimes you discover that your account is empty. We discover certain things, and we have a certain experience of truth. And it's true that here I would certainly agree with Charles Sanders Peirce. In some way or another, we extrapolate.
Okay, thank you very much. Thank you. So I now call on Professor Aditi Lahiri for our second talk this afternoon. Professor Lahiri has 2 doctorates, one from the University of Calcutta and the other from Brown University. Lahiri taught at the University of California before moving to the Max Planck Institute for Psycholinguistics in the Netherlands. And she was a professor at the University of Constance before in 2007 she went on to hold the chair of linguistics at the University of Oxford. She is a fellow of Somerville College in Oxford. She received the Gottfried Wilhelm Leibniz Prize in 2000 and was elected to Academia Europaea in 2007. She is a fellow of the British Academy and served as his vice president until last year. She was awarded a CBE in 2020 for services to the study of linguistics. Her main research interests are in phonology, phonetics, historical linguistics, psycholinguistics, neurolinguistics. She, in her recent ERC-funded project, Morphon, she combined expertise in theoretical and typological linguistics, brain imaging methods, and computational modeling to shed light on the existence and cross-linguistic incidence of morphophonological alternations, diachronic profiles, and processing and mental representation. Our lecture this afternoon has the title, What Doesn't Change? Pertinacity in Language Change and Processing. Professor Lahiri, welcome.
Thank you very much. Do I get the 5 minutes you used to introduce me? Okay, just making sure. We've all been speaking, and we've been speaking in English in a hall which is echoing, with microphones which are kind of iffy. But nevertheless, you've all been trying to understand what's been going on. Most of us are not native speakers. So today I'm going to talk about language and language variation. So if you have the speaker, like me, and the listeners, and the speaker is in charge, you have very little to do to control what the speaker is saying. You've got to make do with what I am saying. So speech sounds are produced with great accuracy, and it's selected from a mental lexicon of thousands. And usually Pim Leveld, former Max Planck director, used to say that 3 words per second, 3 English words. For the listener, there are many problems. You have vocal tract shape, size, noisy, echoey environment, and sounds of the words are not discrete. No word, no single word, not even your own name, if you speak more than once, it's going to be different. No word is ever spoken in the same way by the same speaker. I'm going to play you an example.
It always rains in Oxford, not in Cambridge.
Could you hear this? Yeah, okay. Because over here I can't hear properly. Now this is not true, obviously. I mean, Cambridge rains a lot too. But this little bit,
Oxford.
And this second bit, marked orange,
Oxford.
Now it sounds the same word, with a little rising intonation. But now listen to the whole context.
You need black shoes, wool socks, fur dresses, and a brown hat.
There was no Oxford in it. What you heard was the part of ox, fur, and the de of dresses. I did not manipulate this. You can try it out yourself. Essentially, the human listeners have to segment speech, and unless you're a native speaker, it's awfully difficult. Now, being a phonologist, that's the part of linguistics I focus on, we are interested in sounds. But then, of course, we also have letters, and they are not necessarily in one-to-one correspondence. So the linguists devised what is called the International Phonetic Alphabet to have a one-to-one sound correspondence. Of course, the IPA was based on the Latinate alphabet. What else is new? But then, and they have changed. I'm going to give you some English examples, which you can see that the letter C can be pronounced in different ways. This comes as no surprise, right? But it's not just English. German does the same. In fact, every language does the same after 100 years. In German, you can have a C pronounced as a k or a z, or a s as many other sounds, etc. And Dutch is equally bad. One for only many letters, the reverse is equally true. So, for example, in German, the ch could be written in 2 different ways. In English, the f, the famous Bernard Shaw example, could be fel or cough. Bengali, my own language, doesn't do any better. So if you have the same letter, different vowel, it's difficult to read a script which you're not familiar with, but the bit that's pink, I hope it's pink. Yes, it's pink or purple. And that becomes a ka, but if you change it to k, it's written the same way, pronounced differently. And the opposite is true. You have the same letter sequence, but different letter sequence, same sound. Now, going back to sounds, I'm interested in sounds. So place of articulation, we group sounds together in terms of their properties, which we call features, which may be atoms of speech. So labial, coronal, made more largely with the tongue, with higher frequency energy, dorsal, more with the back of the tongue. The place of articulation, however, of alter, they are never the same. And it's normally called assimilation or absorption of sounds. So examples of place assimilation, so for example, handbag or sunbathing. Now, only non-native speakers like me would say sunbathing, or handbag. That's not the way you go around saying it. So what happens essentially is the coronal sounds, t, d, n, can change to a labial in the context of a labial, and vice versa, sun cream or handkerchief is even written like that nowadays, changes to a dorsal sound. Now, The output variance, therefore, of a single sound can be 3. Na can be na, ma, or nga. Do we perceive these variants? Does it really matter? Well, it does. So I'm going to switch to about perception. So many Latin and Old French words of Romance origin, basically, were borrowed into English, borrowed into all Germanic languages, in fact. And one prefix, the in prefix, which is phonologically written with an in a lot of the time, but the prefix change shape. So for example, if you have an M, it's immoral, impossible. If it's a N, it stays the same. If it is a Ng, K, G, it becomes a Ng. Now, complete assimilation with the legal. Now, as I was going back to saying, does it matter? Can you hear the assimilation? Well, it did. I'm going to go back 14th century, Chaucer. Trust me, I'm not going to, it's only 2 slides of Chaucer. I'm not going to bore you with Chaucer. But this is a text, not a poem. And this is a text, mind you, the scribes are writing. So it's not Chaucer who's writing, right? The scribes are copying the sounds. They're in 2 different libraries. So one is in Wales, and the other, well, you will see in a minute. Now, this is a nice example of impatient, and you can quite clearly see that that's an M. In a very close, similar manuscript, in a different place, different scribe, you look at it carefully, and suddenly it's no longer M, but it's a N, which was the original sound. So essentially, you get the N written with an N. So obviously, the scribe in question must have heard the assimilation and changed the orthography, right? So the labial assimilation is now reflected in writing. Certain things like input are still written with an N, but nobody pronounces it that way. Let's go back to where we were. The point is that this place sort of assimilations are usually asymmetric. There are exceptions, but it's usually asymmetric. So for instance, you can get rainbow to rainbow, but you're not going to get Antrac to Antrac. That's impossible. Okay. So the question then is, given that the asymmetry in synchronic and systems, it is plausible that the asymmetry is an inherent part of the system, an inherent part of our comprehension. Yeah. So how do native speakers cope with the variation? Do we, like Alexa, just simply store everything? No, we don't. That's not the hypothesis I'm going to entertain. I would like to say that the contrast sensitivity is that not all features are stored, but rather you have underspecification of some features. So putting it this way, what does that mean? It means that sounds with a N, I'll just stick to sound N, but it's actually a group of sounds, like sonnet or sonnet, is unspecified for place, while anything with a M is specified for place. And as you will see, the underlying representation for M and the N differ. The N can be pronounced with N or M. Comprehension-wise, perception-wise, the opposite. You can have sunbathe or sunbathe. It should both activate sun, but if you hear Amtrak, you're not going, if you hear Antrac, it's not going to hear Am. Okay, so it should be asymmetric. I'm going to go to the left side. This is harder to see. Okay. These are a couple of electroencephalogram experiments, and this particular one is mismatch negativity. This is made famous by Naitanen in Finland in the 80s. And the basic assumption, if you're my age and you're a psychologist, you would remember these sucking techniques which we had with poor little babies. You put a little sucker in them and you wanted to change the sound, and you wanted to see if the child would change the sound. And you play the same sound, it would keep on sucking, it would go to sleep, and then you play another sound, it wakes up, or it starts crying. Usually it starts crying. But we gave up on that long time ago. This is a sort of thing, like you create a standard stimuli by playing a same sound, and then you tap the underlying representation, which is the deviant, and you want to see whether the brain responds or not. So basically, you're having da, 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 and then you go pa, and then the brain goes whoops. That's the basic effect. We are looking now at, basically these were non-words, this was done in German, And the g and the d should have an asymmetric response. If you hear a g and then a d, you're going to not like it. If you're hearing a d and you see a g, then it may be tolerated. It's sort of like the telephone conversations you have when you're trying to say your name or hear a name and you're trying to correct them. It's certain sounds go, certain sounds don't. So this is the hypothesis. So the stimuli were non-words, but real stimuli, not synthetic. And of course, they were controlled, et cetera, et cetera. The hypothesis was that the conflicting features and that the n and z, in this case, these are specified consonants. Both are specified for their features. They are not placed. They should conflict. However, if you have a g and a d, they should be asymmetric. And indeed, this is what you see. The smaller MMNs that you see, the d to the g, the red bit is giving you a much bigger amplitude simply because they are asymmetric. The other way around, no. In the n-z, they are exactly on top of each other because both are specified, neither like each other. They will throw each other out. Okay. This was in German, but as you know, if you do something not in English, it doesn't go over very well, so we changed to English. And this time it's real words. Here we have words like sonnet or image, and then you mispronounce them into summit or image. So you do it vice versa, right? And again, the notion is that one way, oh, okay, that's a word, the other way, no, I don't like it. So sonnet to poem, no problem. Image to picture should be good. Summit to poem, should it activate or not? Image to image should not. That's the hypothesis. The experimental design, I'm sorry to bother you with this, but this was sort of like you're hearing the sonnet and you're not asked about this word sonnet at all. You're asked about a particular target, which is poem. So you're asked, is this a word or is this not a word of English? And obviously, you get a non-word in control. So it's not like you're giving it to one person. There are at least 48 people, several groups, words are controlled for, et cetera, et cetera. Now, you're expecting sonnet to prime poem. Question is, does summit prime poem? And we are expecting it to be sort of equal, but we are not expecting the other way around. And this is indeed what you find. This is just plain reaction time. Sonnet is primed. Summit also primes sonnet poem. That means it must have activated the real word. Image, of course, primes picture, but image does not. It almost gives you inhibition. Measuring the event-related potential, this time we are measuring the same sort of design, but now we are measuring a component which is best known as N400. It's a component of the electrical activity of the brain which is sensitive to priming, and it is reduced if there is lexical integration. If what you hear integrates with what your brain has, then you have a lower amplitude. So for example, if you have pizza eat, the brain is quite happy. If you have pizza drink, the brain is not happy. So you get a nice peak. And that's essentially what we find. So the first bit that you see is the difference between sonnet and summit. It's fairly low. It doesn't look low over here, but trust me, it is. The important bit is the comparison. And when you see the comparison, you see that there is a huge difference between image and image versus sonnet and summit. So again, there is some asymmetry. We claim that is part of the representation. Now, going back to the native phonological system. Now, not all sounds and properties of sounds behave in the same way. So variation is normal. We have under specification. The native phonological system plays an important role in comprehension. Let's take a step now towards back to Romance loans. So let's now turn to language change. Now, change does not happen in a void. Change happens in acquisition and use, and grammar is being acquired. Okay. So a particular part that I will pay is on loan adaptation. So keeping aside bilingualism, loan adaptations, loan words are adapted by adult native speakers. We're not talking about children. They acquire any language beautifully. We are talking adults. So we expect the adults engaged in loans will be conservative and their own phonological pattern will play a role. Now, this is a nice gentleman whose face you recognize, obviously, and these are the pronunciations of this gentleman's name.
Van Gogh.
Van Gogh.
Van Gogh. Van Gogh.
So the real Dutch is definitely Gogh, right? If you have just going back to German now,
Goethe.
That's the English UK pronunciation. This is a Chicago street name, and trust me, these are real.
Goethe. Goethe. Goethe.
Now you could say these are spelling pronunciations. The German original, of course, many people over here.
Goethe.
But even within the dialects, even it's not just the spelling pronunciation, not just sounds, the stress pattern, the word emphasis of a land, it can change. So mathematics, the A would get stressed in any of the English, standard English dialects, but
Mathematik.
not German.
Mathematik.
Yeah, so that's also in a different word, yeah. So metrical stress is kind of important, but we'll go back to that. Before that, I'm going to play a bit about the sound th. Now, this is not spelling pronunciation, and this is from Indo-European to German. How much do I have? I do have time, okay. So this is old Indo-European to Germanic, like t became a th. And these are the Latin and the Greek and the Sanskrit words. With the t, I'll pronounce the Sanskrit one, trayas, and the Germanic th, Old English happily kept it as a th. Now, this sound should have been banned, but it hasn't been. But Old High German and Middle Dutch, much more sensible, they made it into a d. The Germans, modern German is a d. Middle German, this is inherited, right? This is not loans, this is inherited. However, when you take a loan, then suddenly you have a different pattern. The German borrowing from English is a s, preferably, and the Dutch, preferably, a t. This was found in an eye tracking study where they substituted English th with f and s and t. So thief became thief and thief. And the question was, are they going to prefer one or the other? Now, notice thief is a real word, but putting that aside, words with mispronunciations, would German and Dutch speakers do the same? Well, it turns out that the Dutch preferred a T substitution and the Germans preferred a S. Now, this is an ad from Billets. It's not mine doing.
Das hier ist mein Mindset. Das hier ist das wichtige Gerät des Gewissens. Das Überlebensradar.
Hello? This is the German Coast Guard. What are you thinking about?
Going back to stress. If you take the German language family, the earlier German words, all, without exception, are firmly at the left edge of the word. However, most Germanic languages, and I mean all Germanic languages, have stress on the right side of the word. This happened as a result of many Romance loans. And of course, these Romance loans came at different periods. It started with the William the Conqueror, started with Latinate words first. And then, of course, in English, it came in 1066, and from Dutch and German and Scandinavian languages gradually throughout the centuries. Our point is the following. Although very similar words have been borrowed from very similar languages, they do not necessarily fall the stress on the same place. Take a look at this. These are Germanic words. Now, some of them are compounds. Germanic words are rarely longer than 2 syllables. By Germanic, I mean inherited Germanic. So from bridegroom to peppermint to swallow to widow, it's all initial stress. Take Romance loans. The first line of adventure, Abenteuer, all three languages differ, Dutch, English, German. Sometimes Dutch and English are the same, sometimes German and English are the same, sometimes the other two are the same. Yeah. So the question is, the actual theoretical question is, why did they differ? What happened to the native language at that time that was borrowing? But I'm just not going to talk about that. I'm just going to skip to the modern German and Dutch listeners listening to English. To what extent does their native phonology have an effect on comprehension? So the way we worked this out was just to remind you the inherited words are left-hand side. The two X's are 2 feet, that is 2 stresses, main stress and secondary stress, so Monday and so on. But sometimes in loans, you will see something like reptile versus reptile. Okay, so we ordered them in the following way. The loans that exist in German, in English, but not in German, German disyllabic words, 1 stress in English or 2 stresses in English versus German final stress, so costume versus costume, etc. Or the German trisyllabic stress, so English is disyllabic. English, all disyllabic initial stress. German differs. Question is, does it matter? These were run in England with native speakers of German who've lived there for a long time. Then it was run in Munich with a colleague over here who happens to be in the audience, and it was the same basic result. What we find is the following. So the predictions are the fluent speaker should have no trouble accessing the words. They shouldn't. Nevertheless, their native phonology may have some influence. Can we see the influence? Let's see. So the words that do exist in their native language, the variants may have a difference. If they don't exist in the native language, it would be easier because you won't have a conflict. So again, it's the same sort of task. You hear the fragment this time and you see a word. And our results are as follows. So everything primed, naturally, because there was no problem. They were fluent English speakers. They understood everything, they pressed the button. But there's a difference. And there's a difference is that those words that did not occur in their own language seem to be much easier. Now, if you look at the brainwaves, then you find that there is a significant difference between the words that do not exist and the words that do exist. Okay. You get a much later effect. Going back, actually, the actual constraint is happening only with the words that do not exist, and it depends on how many stresses they are. So you look at this more carefully, you find suddenly that non-existent Germans with 2 feet basically on top of each other. But when you have 1 foot, now this is much lower end 400 because this is a perfect German word. It's a nice German word with a schwa at the end, sort of light syllable at the end and a strong syllable in the beginning. Yeah. We did exactly the same for Dutch listeners, except we added 2 more conditions. One was a native speaker with Germanic stress, and one was just a close match to the Romance word. And you find exactly the same difference in terms of the reaction times, and you find that the Germanic words, they also create a difference because the words that were chosen had a longer vowel in Dutch. I deliberately chose the ones which underwent what is called open syllable lengthening. Those who are linguists will understand that. So hamor versus hammer, and that's the one that you see a prolonged effect, while the same stress also shows a difference. So loans and such, loans with foreign patterns, adaptation is rarely a phonetic match. Usually the foreign sounds are difficult to perceive, let alone pronounce, and it takes centuries to adapt a foreign language. So we have evidence that the native phonology rigorously imposes itself on borrowed words. Influx of loans rarely change the grammar of an adult. And in some, words and word structures vary. They are replete with asymmetries. What appears on the surface is not isomorphic to what is stored in the mental lexicon. Phonological lexical representations are abstract, discrete, not fully specified, and exploit asymmetries. Phonological representations also play a role in language processing and change, and definitely in adaptation. So the native grammar constrains the way in which contrasts are maintained, accessed, and processing, which may reflect in reanalysis in the future. And the people who actually did all the work are here, and not me at all, with all sorts of funding, which we are very grateful for. Thank you.
Thank you so much. One question. In the front. You wait for the microphone. Wait.
Thank you for the fascinating lecture. Those loans you talk about, do they occur between languages that don't share a common script or alphabet? I think you showed it on one of your last slides, but it was really fast. Meaning like, say, I don't know, Russian and Germanic languages, or Mandarin and English. Could you comment?
They should differ. So whether it's Germanic speaker or a Russian speaker listening to the same sound. Is that what you meant? Sorry, I didn't.
These loans happen. You talked about these loans.
Yeah?
Between the Romance languages and the Germanic languages. In history, do these loans happen between languages that don't share a common script?
Of course. And so, for example, Bengali borrowed loads and loads of words from Portuguese and from English. Mandarin from Japanese, or rather Japanese from Mandarin throughout the 3000 BC stage when there was a... So it doesn't, I don't believe it has anything to do with the script, because most of the people didn't speak and the language, didn't write the language at all. The script is a much later phenomena. So I showed the examples of Van Gogh might be spelling pronunciation, but most of the time it is not. So when Bengali borrowed from Portuguese, all the written T sounds became a T in Bengali, like a dental T. All the English ones became a T, and the alveolar sound became a retroflex. So they heard it, they didn't read it.
Thank you so much. And we now move to the award of the André Mischke Prize, and I call on Katalin Solymosi to introduce us to the awards.
Thank you, Paul. Can you hear me? So, as Paul said, I'm Katalin Solymosi. I'm a plant biologist from Eötvös Loránd University, Budapest, Hungary, and I am also the newly elected chair of the Young Academia of Europe. First of all, I would really like to thank Academia Europaea and especially Maria Makarov and Don Dingwell for helping us to co-organize our annual general meeting and the Building Bridges conference with Academia Europaea. And we really like, this is a fantastic conference, and we really like this excellent new format in which the speeches and each session are integrating Young Academy of Europe and Academia Europaea speakers. So now I would like to present, I have the honor to present this year's winner of the Young Academy of Europe, André Mischke Prize for Science and Policy, Professor Renaud Jolivet. It will be Scott Bremer, the Vice Chair of the Young Academy of Europe, who will give the laudation. Scott, the floor is yours.
Thank you, Katalin. The Young Academy of Europe Prize, first introduced in 2017, is awarded annually to early to mid-career professionals in recognition of their outstanding achievements and contributions to the key areas of the Young Academy of Europe. In 2019, the YAE Prize was renamed the André Mischke Prize for Science and Policy in honor of the YAE founding chair, André Mischke. The prize is awarded to support and promote excellent active scientists who make important contributions to evidence-informed policy-making at European level, science communication and outreach between scientists and the general public in Europe, and strengthening network and support between and for the future generation of scientists and scholars in Europe. It is my pleasure with Katalin, on behalf of the YE Prize Search Committee, including the outgoing chair Monique Trump, who unfortunately couldn't make it, to announce that this year's André Mischke YE Prize for Science and Policy goes to Professor Renaud Jolivet. Professor Renaud Jolivet is currently a full professor at the Maastricht Center for Systems Biology and chair of Neural Engineering and Computation at Maastricht University. He currently holds a courtesy appointment at CERN, the Particle Physics Laboratory. He is an elected member of the Board of Directors at the Organization for Computational Neurosciences and the inaugural chair of the Science and Technology Committee of eBrains, the European Research Infrastructure for Neurosciences. In 2023, he is also a Neurotech Fellow at the Foresight Institute. He has worked in Switzerland, Japan, the Netherlands, and the UK. His work focuses on the brain's heterocellularity and on neurotechnologies to interface with brain tissue. Over the past decade, Professor Jolivet has also been active in science policy at the European level, at different levels and within different organizations. He was first part of the various working groups of the Marie Curie Alumni Association before being elected to the board of the association for one term. From there, he served as the MCAA representative on the board of the Initiative for Science in Europe and as external policy advisor. This work has led to a number of important policy documents published by MCAA and ISE, for example, on research precarity, and to a number of policy workshops and sessions. Many of these topics have now been taken forward by the European Commission in new policy and initiatives. Since January 2022, he is representative for individual researchers and innovators at the European Commission's ERA, European Research Area Forum, to which he was nominated by the ISE, MCAA, Eurodoc, Euroscience, and the Association of ERC Grantees. There, together with his colleague, Professor Dr. Agnieszka Wajkowska, he brings the voice of researchers to the table where the future of European science policy is crafted. YE is proud to present this award to Renaud to celebrate his excellent science, as well as significant and impactful contributions to European science and policy. Please come forward to collect your award and present your lecture.
Yeah, okay. I need my slides though. Yeah. All right, so thank you. Yeah, so first of all, I would like to thank the Young Academy of Europe for giving me this award. I'm incredibly honored and humbled to receive this award. I didn't have the chance to meet André Mischke, but upon reading on his life and his career, I realized that we crossed paths unknowingly on many occasions, and in particular maybe at CERN. And his shoes are pretty big to fill, I assume, but I hope I will be able to continue being active at the interface between science and policy and somehow to continue his legacy in some way. So upon preparing for today, Monique, who couldn't be here, unfortunately told me that I should be talking about my science, but also about my activities in science policy. So this is the plan for today. These things are relatively difficult to connect, but I will try to do an awkward transition somewhere in the middle there. I'm a neuroscientist, and I'm interested in trying to gain a mechanistic understanding of how brain networks function. And what you can see here is a couple of neurons that have been imaged in the cortex of a rodent using calcium imaging and two-photon microscopy. And you can really visualize the electrical activity of these neurons. And so when you look at these kind of images, it's tempting to think of the brain as a very large neural network, and it is indeed what how many neuroscientists see the brain. But since very early in my career, I was really fascinated by this question, which was really, is that really all there is in the brain? And in fact, it was partially motivated by a lack of confidence in my abilities, because I thought people have been working on neural networks for the best of 80 years or something, and we still don't understand very much about how they function, so what could I possibly contribute? And in fact, there is an issue, I think, in neuroscience that I like to address often and very regularly, which is that we don't really have a full appreciation for the diversity and the complexity of this organ. And you can appreciate some of it on this cartoon rendering or artist rendering of a brain at the cellular level. And you can see that there's a lot of stuff in there, right? There's a bunch of neurons, but there's also a lot of blood vessels. And there's these cells that are drawn in blue, which are collectively called glial cells. It's actually an umbrella terminology for many different subpopulations of cells. And if we zoom out, so you can start to appreciate, I think, the complexity that we are facing if we want to understand or to gain a mechanistic understanding of what is going on in these brain networks. And if we zoom out, this is artist rendering of a cortical column in the cortex of a rodent. It spans the full thickness of the rodent's brain, and you can really appreciate the mess that it is and this complexity of cells being intertwined with each other. And in fact, the central problem that I think we have in neuroscience to an extent is that about 80% of the cells in the cortex in humans are not neurons. So while we like to think of the brain as this very large neural network, it is actually a very narrow view of how the brain works. And we know that these cells have very interesting properties. We know from system-level studies that they are involved in cognition and decision-making. And we also know that they play a significant role in pretty much all the diseases of the brain. And they have some interesting physiology and properties. And I showed you just before how these cells, neurons can be active electrically. So these cells are not necessarily active electrically in the same way that neurons are. And here you can see a 3D rendering of a cell we imaged. This is from work I did at UCL some years ago. This is actually a microglia. It's a subcategory of glial cells. And you can appreciate on the left at least the really beautiful and complex morphology of these cells. And as I said, they are not electrically active like neurons are. But they display really interesting behaviors. And you can see one of these cells on the left imaged in the tissue, extending and retracting branches and being essentially mechanically active. And you probably don't think of your brain as a place where a lot of mechanical activity is taking place. But there are millions of billions of cells like this in your brain at this very minute, which are probing and scanning their environment. And on the right, you can see how they respond to any kind of injury, which was here we just destroyed a piece of tissue using a laser ablation. And they immediately detect that something is going wrong, and they immediately extend their processes to try to completely circumvent or restrict the area of damage and to prevent it from spreading. So I've been fascinated by these cells for a very long time. And I think that somehow we need to embrace that diversity in brain science. And that's why I sort of renamed the name of our field to brain science and not neuroscience. And I think in neuroscience today we have 4 big research directions, which are trying to understand the brain, healing the brain, interfacing with the brain, which is, as of the last few years, has become a very hot topic, but also mimic the performance of the brain in what is called neuromorphic computing. But in my view, we will not be able to really fulfill any of this research program unless we really map these uncharted territories, so these 80% of cells that we don't really account for at this moment. And as I said, we know that they are important, but we are lacking a computational framework like we have for neural networks to really try to understand how they mechanistically influence and play a role in the activity and sometimes the pathophysiology of brain networks. The other problem that we have, in my opinion, which is a kind of a large-scale science policy question, is that I think we are slowly running out of questions that can be addressed in small university labs in neuroscience, and we really need to move towards large-scale neuroscience. And this is the reason why I'm involved in eBrains, which is a large-scale European research infrastructure for neuroscience. I don't think that this is the full answer to the addressing really this problem of complexity, and I think we will need to borrow strategies and methods that have been employed in other fields. And we heard earlier today of large-scale initiatives in astronomy, but also in geology. And I think we need to move towards these kind of solutions. So how do we try to bring in these non-neuronal cells in the kind of framework, or how do we try to develop a theory for these non-neuronal cells? And it's pretty difficult because they don't have an activity that is easily identifiable and modeled like neurons do, because neurons generate these electric pulses which are relatively easy to put into mathematical equations. But one of the roles that is well identified for these non-neuronal cells is the fact that they metabolically support neuronal activity. And this is really relevant because the brain is actually a pretty greedy organ. So if you look, if you try to measure the power consumption of the brain, you will find out that your brain as an adult has a power consumption of about 20 watts. So this doesn't seem like much because it's the power consumption of an old-fashioned incandescent light bulb that no one is really using anymore. But it's about 20% of your body's energy budget, while the brain is only 2% of your body weight. So the brain is actually a pretty greedy organ in terms of energy consumption. And it's even worse during development, or worse, it's even stronger during development. And we know that this has significant behavioral effects. And there's a paper, there are a number of studies that show that, but there's a paper I really like to mention often from Herculano Hausel and colleagues, which is not mentioned here. But what they did is to look at the body weight and size of the brain of large primates and to try to measure how much do they need to spend every day feeding on a raw vegetarian diet, so basically munching leaves and branches in the forest, in order to be metabolically able to support their large bodies and large brain. And gorillas have brains that are in size, in terms of the number of neurons, are relatively comparable to ours. And what they found out is that they basically need to spend 8 to 9 hours a day feeding in the forest. So of course, it's a huge behavioral constraint because it doesn't leave you very much time to develop a culture, to develop tools, or to develop an advanced language maybe. And so we know that this energetic, the energetic cost of the brain has some important consequences at the system level. So now, a couple of years ago, we were interested in addressing these questions with my colleagues in London. And so what we did is to try to look at how information flows are balanced with energy savings in neural networks. And so we looked at a first hypothetical scenario. So you know that neurons are electrically active. They generate these pulses that are called action potentials or spikes that are sent down their axons. So this is how they talk to each other. But when this electrical signal reaches a synapse, then you have a chemical neurotransmission. So you have some molecules that are released and that activate the next neuron in the chain. And in fact, the propagation of action potential is relatively reliable, but the release of these chemicals at the end of the chain is much noisier than you would think. And it can be as noisy as, you know, having a 20 to 40% actually probability of release. And so this is a bit weird because this is definitely not how you would organize the system from an engineering point of view, let's say. So what we did is to develop computational models. We mixed information theory with biophysics. And what we found out, there's in a relatively trivial scenario, is that if you want to maximize information transmission, obviously you want to have a release probability, so a communication probability that is very close to 1. So you can't really explain the physiology based on this argument of maximizing information transmission. But if you look at the ratio of information to energy consumption, what you find out is that you can actually, I can explain the math maybe later, you can actually get these kind of curves, and the optimal energetic design, so bits of information per ATP molecule, if you want to know, is usually close to a very low percentages. And so it suggests that this organization, although it doesn't seem to be very efficient from an information processing point of view, it finds the right balance between information flow or managing information flow and the concomitant energy consumption. And so what we did next is to bring that into experiments, and we did that in the rodent brain. I mean, this is illustrated here with a human brain, but we looked at the information flow in the visual pathway, and there's a relay synapse between your retina and the visual cortex, so information doesn't go straight to your visual cortex, it passes through this relay synapse first. And you can experimentally manipulate the synapse, and when you stimulate the synapse or you stimulate the gain, you tweak the gain of that synapse, you find out that at the physiological gain 1, this data is normalized. This is usually where your synapse is actually sitting and where you have optimal energetic design. So it doesn't need to be like this. And in fact, it's not like this for every cell we recorded from. But in average, and in the great majority, what we find out is that most cells seem to find the right balance between information flow and energy consumption. And now this poses a bit of a conundrum because you would expect that the network is optimal, and that doesn't mean that would not necessarily translate into optimality for every component of the network. And so how do you reconcile these two things? And so very recently, so these results are a bit rough because they are from literally the last few weeks, but I have two really gifted students in my team, Dima and Emeshe, who've developed a synaptic learning role that is trying to balance information and energy consumption. And so what you are seeing here is a measure of the level of activity in the network when we crank up the intensity of energetic constraints. So we are asking the synapses to learn, but to try to save energy on the side. And so what we observe is what you would expect, because eventually that's what the learning rule is implementing in the network, is that you get activity in the network that is sparser with fewer spikes, but you also have weaker connectivity in the network overall. And what is very interesting to me is that even though you would think that this would normally decrease the level of inference or the maintenance of information between input and output in that neural network, what we observe is that initially it actually improves inference. And so there seems to be a benefit to implementing this additional constraint using this synaptic learning rule. So there would be much more to say about this. And what we were able to show, so I pointed out just a couple of seconds ago, literally, that in experiments that we did when we sampled neurons in the visual pathway, we found out that each one of these neurons seemed to be optimally tuned, and that this physiological gain of 1 seemed to be the gain that maximized the ratio of information to energy consumption. And what we find out is that when we apply this learning rule, but we don't implement any energetic constraints, synapses are suboptimally tuned, but when we do implement energetic constraints, we recover these experimental results that we had previously. And so this is really exciting to me because this is basically, we recovered the experimental results that we had from several years ago, essentially for free in that study without having to build it in the network. And so how does that connect to these non-neuronal cells? So the synaptic learning role that we devised is a so-called a three-component learning role. It has a presynaptic and postsynaptic component. This is usually what happens because you expect that neurons that are connected to each other, whenever they fire, their individual contribution comes into play, into modulating the intensity or the intensity of the connections. But there's also a third component in that learning role that we think can be directly connected to the role of glial cells and astrocytes in that case in particular, which are a subtype of glial cells. And we think that this third component can be directly connected to their well-established role of maintaining energetic balance in the network as a whole. And so we think we are on our way somehow to a holistic view of brain networks that expand beyond a mere description of neurons and neural networks, but what we like to call neuroglial networks. And we are essentially using this energetic or metabolic constraint as a guide to devise this theory. So this is definitely not the end of the story, but I hope I convinced you that there's some benefit to actually looking at diversity in the brain and to looking at diversity in terms of how the different cell types in the brain contribute to brain physiology and pathophysiology. All right, so that's it for the science. Now I would like to say a few words about my science policy activities because I think that they are important things to say. So I I'm a first-generation academic, so diversity is a topic that is dear to my heart. And actually, when I was much younger, I thought that it would be very important if I ever get a lab that I get engaged in mentoring early career researchers. And this led me on essentially a second or alternative career. So I was first engaged mentoring early career researchers. That led me to the Marie Curie Alumni Association, then to the Initiative for Science in Europe, and finally to the European Research Area Forum, where I sit today, and where I represent individual researchers and innovators. And for those of you who are not familiar what the ERA Forum is, it's a new format that the European Commission has set up, basically in January of last year, where the European Commission, member states, and representatives from stakeholder organizations are involved in discussing science policy at the European level and shaping science policy at the European level. So this has been a very interesting learning experience for me. And I think there are 3 points that I really want to make today about my activity there. The first one is that I think that it's very important for us academics to engage with politicians and policymakers, and we definitely don't do enough of that. And I feel that often we leave that space for other people to move in, who don't necessarily have skin in the game, or who don't necessarily have field expertise or have experienced what it is to be an early career researcher or even a senior academic at a university or at a research lab. And I think that academia today is changing very rapidly, and it's really important and necessary that we have active scientists or recently active scientists who are really sitting at the table and helping these people in shaping policies and interacting with politicians and policymakers. And this shouldn't be construed as a criticism from of my colleagues at the ERA Forum. I think that they are smart, competent, and they mean really well. But we also fail in that effort to communicate to them because we don't understand their language, and we also don't make any effort, I feel, to understand the constraints they operate under. And I think this is really important. The second point I want to make and that I've learned is that the landscape of science policy in Europe today is incredibly fragmented, and I think it's a great tragedy of science policy in Europe. We are unable to speak of a relatively unified voice, and we see the consequences. The farmers are better organized than we are and manage to get huge subsidies, and science, which I think is extremely important, and research and development, which are extremely important, are not being funded to the level that they should be. And often you see a lot of university associations and associations representing early career researchers speaking with each of one of them pulling into different directions. And I think really what I want to say is it's basically a call to action that I think we need to be better organized and to try to preempt that by agreeing upon ourselves, among ourselves, about clear policies that we want to see implemented and communicate with to the European Commission and to our member states with a more unified voice. And I think this is the last point I want to make, and I will be on time, is that I think that there is extreme urgency to do that. We are facing, obviously, immense global challenges. One of them is climate change, of course, where science will be crucial in finding some of the answers and addressing some of the issues. But I think that I'm not sure all of you are aware, but surely you will have remarked that we are living in dangerous geopolitical times, and change is coming. And I was last week at a meeting at the European Commission in Brussels, and I can tell you that there is a whole legislative arsenal that is being put in place in our member states and at the European Commission. And I think the era of open science and free communication that we've all grown in science is probably coming to an end. And it will have a huge impact in the years to come on what kind of research we can do, how it is being organized, and this is especially true for certain technological areas, but also with whom we can do that science. And I think we need to be really proactive in shaping that agenda, because if we don't do it, we might have to live with consequences we don't like very much. And yeah, so this is really my point of view at the moment on our efforts to really try to sit at the table and to shape the political agenda at the European Commission. And with this, I will conclude. So I would like to thank my colleagues and collaborators. I have a second career in life in science policy, and I've had the chance to make a lot of friends and great colleagues while working in science policy. And thank you for your attention.
I think we do have time for just one question, Professor Jolivet. Yeah.
Well, thank you very much, Renaud, for that extremely elegant talk. I just had a quick question about your thoughts on energy consumption by the neural networks at rest and during activity. I know this is all at the cellular level, but do we have in vivo methods to analyze the differences? And we know that
sorry, the sound is really bad. I didn't really hear what you said.
Oh, do we have methods to look at energy consumption and brain networks in vivo? And if so, do we know what's the sort of main difference in energy consumption between a resting state and a sort of...
No, so metabolism is pretty hard to accurately measure in vivo, right? Or even in situ in brain slices, especially at the cellular level. So you can have you can easily measure things at a rather system or macroscopic level, but that doesn't really give you the kind of granularity that you would want to have to really look at what happens at the cellular level. There are some experiments that Kazishkate published in Science many years ago where they used 2-photon microscopy, but they have been criticized on methodology. So I think it's pretty difficult. So that's why we use biophysical modeling, because we think we have a better handle really on the mechanisms that we know account for high energy consumption in the tissue, right? So basically activation of ion channels and postsynaptic receptors. And there it's pretty easy to convert the electrophysiology of the cell into some kind of assessment of ATP molecules that the cell needs to power itself or to power these mechanisms. So that's the kind of approach that we are using. We would be, of course, very interested in trying to, having more concrete experimental measurements, but they are usually technically very difficult to get. Yeah.
Thank you. So it's time for our last coffee break. Please be back at exactly 3 o'clock. Welcome back to this last session, where we will first have a lecture by Professor Horst Bredekamp. He received his doctorate at Marburg with a thesis on art as a medium of social conflicts. He went on to become a professor in Hamburg and later Berlin. Since 2003, Professor Bredekamp has been a permanent fellow of the Institute for Advanced Study in Berlin, and he has the Gadamer Endowed Chair. Bredekamp was a fellow at the Institute for Advanced Study in Princeton, and the Getty Center in Los Angeles, the Collegium Budapest. Professor Bredekamp is renowned for his work in the field of image science and the role played by visual argumentation during the scientific revolution, with a focus on images such as those used in the works of Galileo Galilei, Hobbes, Leibniz, Charles Darwin. Much of Bredekamp's work has been translated into other languages, including English, French, Spanish, Italian, Chinese, Japanese, Portuguese, Romanian, Estonian, and Hungarian. The title of Professor Bredekamp's lecture today is From Global Art History to Active Matter. Please.
Thank you very much for this introduction, dear members and guests. About 15 years ago, an international symposium on the future of art history was held at the Clark Institute's Art Historical Research Center in Massachusetts.
It is a venue similar to the Getty Center in Los Angeles, with a magnificently endowed foundation that gave rise to high expectations. It was discussed to what extent art history would become a kind of second archaeology on the occasion of the new media, and in what way it could meet this challenge. My own contribution was met with incomprehension, and it quickly became clear that this was due to the different traditions of the history of images and the history of science. I argued for a universal history of art as a history of images that goes back to the early history of humankind, as well as encompasses the entire globe, that is, for both a vertical determination of depth and a horizontal encompassment. I referred to Franz Kugler, who received his doctorate from the Berlin University in 1831 with a thesis on medieval book illumination, and later also habilitated with studies on the art of Islam, Egypt, and India, to be appointed professor at the Berlin Academy of Arts in 1835. At the same time, he also taught at the university. Lastingly inspired by Alexander von Humboldt's worldview, Kugler united and distinguished all the visual cultures of the world known to him in his, to the right, Handbuch der Kunstgeschichte, Handbook of Art History, published in 1842, and did so without privileging Europe's position. Kugler's history of art was not only based on its earth-encompassing vastness, but also on its temporal origins. The illustrated edition of Kugler's manual, published in 1851, shows the outline of his material. In the first illustrations, Stonehenge, for example, is relatively clearly visible. According to Kugler, the spiritual penetration of matter that leads to form is already developed in this very early period, with all the forms of, quote, sublimity of measure, even of harmony, Erhabenheit des Maßes, selbst der Harmonie. With impressive self-evidence, Kugler begins his history of art with deliberately hewn and collected stones, that is, with the material and with the reflection of the possibilities of art that are at work in it, in a world and time spanning general history of art as visual history. The possibility of such a world history of the image seemed to be magnificently opened by the sheer shock of the discovery of the cave paintings of Altamira in 1879. It seemed fraught with references to contemporary art, like in the form of Impressionism, but this chance was squandered. As Ulrich Pfisterer, whom you know, who is member of this academy, but he is ill, as Ulrich Pfisterer has vividly described it, the idea that these first testimonies weren't art, but a kind of pictorial language, and were not purposely in the design of form, but instead magical practice, played a weighty role for the separation of the entire field of prehistory from that of art history. With this approach, the art of the so-called primitive peoples, Naturvölker, that Kugler had included, thus no longer belonged to the canon of an expanded art history. What I presented at the Clark Institute was a dream directed from retrospection into the future. It was not, I hope I can say it so, a lip service. I tried to give it, perhaps vainly, a reality through attempts to reconcile art history with anthropology. Today, I would like to develop, from my own experience, an updated version of this dream that responds to the contemporary claims of art history as a universal visual history. I come to my second of 4 points, the indigenous as a standard. Against this background, it is worth recalling 2 scholars on both sides of the Atlantic who tackled the horizontal perspective of a global art history and who drew profound methodological consequences from the expansion of their field of vision beyond Europe. During a period of fiercest nationalism, Arthur Kingsley Porter, professor of medieval art at Harvard University from 1921 until his unexplained disappearance in 1933, succeeded in exploring an alternative with his multi-volume publication of the sculptures of the pilgrimage routes to Santiago de Compostela. The work mocked the national borders, ignored geographical barriers, and was linked to questions whose meanings ranged from pedagogy to the magical elements of religiosity. His defining experience had come in 1914, when he and his wife had studied indigenous cultures north of Ontario's Lake Superior in areas unknown to Western eyes. Porter drew his fearless rejection of linear perspectives like nationalism from this experience, as Kathy Brush has shown. Nearly 20 years earlier, the well-known Abi Warburg, whom Kingsley Porter revered, had moved to the Pueblo Indians of New Mexico and Arizona to study a culture that captured his notion of the scope of art, his Umfangsbestimmung. His conception ranged from bodily gestures to tattoos and body-expanding jewelry and devices to symbolic artifacts and artworks of all kinds to grasp the profound connection between nature, violence, distancing symbol, and design. As a child of his time, he brought some beliefs and performed actions that would be unacceptable from today's perspective. It was all the more significant that he returned from America with a concept of world art that was based on the symbolic world and culture of the Hopi Indians. What has been largely overlooked is that his legacy, the Mnemosyne Picture Atlas, has its energetic core in this indigenous reference. To James Mooney, the eminent Comanche scholar, Warburg professed in 1907 that his Hopi experiences were the fluidum that had governed all his research on the European Renaissance. Without them, he would have been, I quote, incapable to find a larger basis for Renaissance psychology, end quote. When Warburg believed he could finally complete the picture atlas in the late 1920s, he planned to travel to New Mexico a second time in order to find closure. Fittingly, it is currently the Florentine Uffizi, here you see one little sector, that feature an ongoing exhibition on the picture atlas. So when you go to Florence, please go and see it. For the first time, it conveys, with the help of ancient American material, the extent to which Warburg, the self-confessed, I quote, Jew by birth, Hamburger at heart, Florentine in spirit, end quote, that he also had become, as he put it, an, quote, Indian soul, end quote, in order to form his theory of visual history and ethnology. In the course of recent discussions of a global art, historical asymmetries of the colonial epoch have been brought into focus. Herein lies a necessary element of a historical reconstruction on a global scale. But in this frame, the visual history goes beyond it. Warburg attested to the artifact an image vehicle, Bilderfahrzeug, with its own energeia, a potential that eludes the dominant power relations and can act both within them and subversively. It is this potency of images that calls for a global history of images that is decidedly more than the echo of power relations. My third point, iconic turn and methodological universality. Both Porter and Warburg combined forms of analysis that employed a concept of world art in any field in the sense of Johann Gottfried Herder's and Wilhelm von Humboldt's relativistic definition. When Gottfried Böhm in 1993, with his coining of the term iconic turn, called out to philosophy that without reflection on images, it would not be possible to understand and conceptualize the world, he envisioned such a comprehensive validity of the concept of the image from the prehistorical hand axe to the virtual simulation. With his formula, iconic difference, he consequently focused on a phenomenon that assigns to the image a peculiarity that cannot be seamlessly incorporated into the historical and cultural frameworks that lie outside of it. I myself have tried to place alongside this a definition of the image that does not proceed from the potentiality and activity of the viewer, but from that of the image. It does not break down the world from the individual, but is broken down by the object itself. As Jan van Eyck's portrait on the framework is to be seen, expresses it on the upper frame, as I can, and on the lower one, Jan van Eyck made me, the picture speaks. The work speaks in the first person singular. The image as a fixed entity thus becomes diffuse, potent, and in so doing, it allows a bridging to image conceptions, aesthetic experience, and heuristics of those indigenous cultures that assume indispensably an active role of artifacts themselves. My fourth and last point, image activity and the activity of matter. At present, in the course of the material turn, this concept is invoked in a remarkable reshuffling of the relationship between nature and culture, in which the experience of the image becomes one of the guiding models for the redefinition of matter, from the image act to matters of activity in general. A cluster of excellence at Humboldt University, of which I am one of the speakers, is dedicated to this context. It is an extremely challenging problem, as Charles Sanders Peirce has depicted it in a wonderful drawing, to place in the center the question of activity itself and its epistemological underpinnings in all fields, from astronomy to nanotechnology to bacteriology. Here in the picture, it's a photography of Regine Henge, the biologist, to medicine and to the humanities. The talk of Dieter Braun this morning was full of it, naming, for example, chirality and symmetry break and other phenomena. It is necessary to seek a new concept of matter. A real symbol of intrinsic activity is the pine cone, which, detached from the tree, freezes into liveliness within short. Life has gone out of it. Why? When moistened, it then begins to move again, could initially be attributed to the external influences of the air and envelope. Current wood research, however, asks whether an intrinsic structure, a system of codes, must remain dormant and latent in the matter itself in order to be able to react of its own accord to these external influences. If this is indeed so, then the sharp distinction between dead and living matter would no longer be clearly given. Researchers like Peter Fratzel, Material Studies, today come to the conclusion that passivity can in no way account for the actions of the scales of the pine cone and below. Rather, respectively to this kind of unfolding itself implies a structurally implanted sign of activity. From here arises the bridge to the most advanced movements in contemporary material research, which rediscover concepts of active materiality and the seemingly passive thing, dem Ding. Technologies are no longer based solely on the ideas of passive natural objects and materials, but of things that themselves become physical, biochemical, and symbolic agents, thus intrinsically reinforcing the determination of objects, from things to objects, Latin obigere, they come against us. A significant field of investigation in this framework of the biofilms already seen, as I said, from Regine Henge, which in the form of myriads of bacteria from extracellular architectures in the smallest of spaces and which, with an impressive intelligence, unfold a morphological autonomy that leaves the observer astonished. They are self-regulating micro-architectures that give rise to geometric patterns. According to the classic doctrine, they are also mainly caused by external effects. Under the changes of the pressure of heat or the growing cold, these bacteria contract or expand. This is a common interpretation. But there remains here, as in the case of the pine cone, a rest that points to an idiosyncratic, structurally conditioned self-design that depends on a common code. One of the strongest challenges of contemporary fields of inquiry in the natural sciences assumes such comprehensive activity ranging from bioforms to seemingly dead things. The rise of this notion of material activity unfolds out of the laboratories of the natural sciences in parallel, but also in part together with image activity, a physicality of its own, changing the very concept of culture. Technologies are no longer based solely on the ideas of passive natural objects, things, but of things that themselves become physical and symbolic actors, thus assuming the definition of objects, as I said, and counteracting any form of dualism. Conclusion. Sorry. The magic word of the present natural sciences, active matter, the magic, not world, perhaps also world, the magic word of the present natural sciences, active matter, is linked to a concept of the design of matter that corresponds to the status of the image as an active and not only visually perceived entity. Within this framework, the possibility, if not the imperative, arises for the history of art and visual history to take up the most radical expansion of Gestalt philosophy to date, as undertaken firstly around 1800. A general morphology that places the activity of form at the center of analysis, irrespective of the distinctions between organic and inorganic nature, as well as natural and artistic design. On this basis, might a truly encompassing and global history of art as visual history may be defined as might be possible, defined in this larger frame by a sharp distinction, of course, but the frame, but I talked about this general frame. This kind of visual history would take along the fluid transitions from the activity of natural to artificial forms. Such a global visual history would not paratactically place the different image cultures next to each other in an additive or superimposed way. It would rather try to take a look at the relational structures and the unpredictable, the untamable, the violent and the subversive, the oppressive and liberating potentials of the form as such in nature as in art. You may call this a romantic return to the time when Johann Wolfgang Goethe formulated his all-embracing concept of morphology, the most radical ever brought forward. But instead, surprisingly, such a concept of the image comes close to the most advanced considerations of material research. In this, my dream expressed at the beginning may have a higher degree of realization than it may seem. Concepts such as the one Franz Kugler set with his handbook of 1842 remain virulent as a universal visual history of the artifact which does not place man in the center, but teaches him an active world of form and matter. Thank you.
Wonderful, and this actually provides us with time for a real Q&A. So I call on the room. Who goes first? There we go. Wait, just hang on.
Many thanks for this wonderful presentation. I am in literary studies, and I think the same thing is happening with literary form, that the form is all. My question is, does the role of the observer change? I mean, who is to perceive this active matter? Is it important, the attitude of the observer, or not? Can you hear? I am asking about the role of the observer. You have an image that is active, but does it mean that it requires a special kind of attention to capture the essence of the painting, or not?
No,
to make it simple.
Yeah, this is the very central question which has to be put. And behind your question, of course, there is the Kantian philosophy, the worldview. I, as an ego, construct the world, and so I have to put my into the center, my view into the center, and see that it is a relativistic one. I am, of course, a Kantian, but also an anti-Kantian. And I think that the worst thing that he has done, that he threw Leibniz out of the window. And coming from Leibniz, referring to Leibniz, what I try to talk about is in the center of the worldview and philosophy, against dualism. The modern is spiritual but has a body. And from there you might come to Spinoza. Who is shaping the form? No existence without form. What explains the effect that each form goes beyond itself? That is the teaching of Gestalt philosophy, and that is why one can say that the Gestalt philosophy as a driving force is the very force in the universe from the Big Bang, if the Big Bang ever existed. And in this frame, that what comes against us is essential, notwithstanding that you have to relativize your own standpoint. No doubt about that. But there is something outside which takes me as a prisoner and not I the world. And because this has been forgotten in the so-called Western culture, we have the disaster which we are in this moment. And that's why I plead both for a Gestalt philosophy that takes the activity of matter and goes beyond it. This is my last sentence. I adore Aristotle, but he was the one who argued nature is passive and feminine, spirit is active and masculine. And that is the worldview that has destroyed the globe. And against this, I plead with Leibniz for an anti-dualism that does not differ between these two poles. And that was my point.
Thank you very much.
Yeah. Do we have a second question? Yes, over here.
Yeah, thank you very much, dear Horst, for this impressive tour d'horizon through a lot of material, offering also a lot of methodological insight. I wonder how you view digital imagery in this methodological context. So you talked about active materials, and as you probably know, there are also many researchers nowadays doing research on tangible digital worlds. So through the illusion of touch, using creating force feedback, and with an active change of their physiognomy, now pushed by AI programs. So I wonder if and how does that fit into the methodological approach you presented, or is there the old difference between physical and virtual reality still there?
It is powered with matter, you know, very costly ones, very heavy ones. It is matter. There is no simulation without matter. And that's why I would never radically distinguish between analog and digital. The digital has matter. That was the discussion in this morning after the talk about the twin culture. All voices argued, sorry, there is a body in this simulation. The question came from Oliver Grau, who wrote about this question, discussion, a dissertation, and I think answered it in an absolutely convincing way. I'll give you the answer back. The distinction between the digital and the analog is an ideology that is also dramatic. It is a deep-going pushed by the great enterprises, digital enterprises, that you save the world when you put it into the digital. The greatest climate changer, the climate catastrophe supporter is the internet. The internet in these weeks will cost more energy than China in these weeks. Many physicists talk about it. There was an article in the Spiegel. So to distinguish between the digital and the analog is an ideology that brings the world into an abyssus. And that's why I would include the whole world of the digital as a seemingly tactical one into the great frame, perhaps too great, which I tried to expose.
That's an intriguing point to bring this to an end. Thank you so much. Yeah, sorry, there you go. Right, so we move to the next presentation, which includes me, so I'll have to chair myself, but it is really a presentation of the results of the task force, so I call on colleagues to come up here. There we go. Peter. So the introduction must be made by Professor Peter Wagner.
Okay, thank you very much, Paul, even though you're yourself involved. Well, you will have understood already that this is not a lecture or presentation like all others, but what we will be doing is to talk about, to report if you want, but also to propose about the Task Force Environment, Sustainability and Climate. So what I will do, I will give a brief introduction in, I have to put this here, I think, in 4 short points. Some of you, those who have been at earlier meetings, especially Building Bridges 2022 in Barcelona, will be a bit familiar, but most of you will not. So I think I will not be repeating very much, or in the worst case, reminding. So the first point is the initial assumptions. This goes back to roughly 2 years ago, when there was a debate about there being issues of global reach and global urgency, for which Academia Europaea has specific expertise because of its all-encompassing interdisciplinary nature and because of its transnational remit in Europe, but also beyond Europe. And that for these reasons, one should explore whether there are not, whether steps should not be taken, that Academia Europaea should identify such issues and express itself on them. They are actually, when Horst Bredekamp mentioned the disaster and in his concluding remarks in response to questions, that is actually what you could say is one of those issues. So the second step then was the exploration, the identification of such issues. What we did last year already in 2021, a preliminary task force was appointed with indeed the task of first of all exploring. What we did was we did an online survey among all members of Academia Europaea with a rather good response rate, asking about questions relating to ecology, broadly understood, environment, sustainability and climate. And we took several insights from the responses, which could both be quantitative and qualitatively analyzed. The first insight was that there is indeed a high level of consciousness and concern, as well as of commitment among members of Academia Europaea about this issue. Second, more substantively, a key issue was what you could call the science public interface, the science communication, as someone expressed it, someone from the exact sciences. The knowledge is all there, but there is no successful way of communicating this knowledge and lead into action. So questions of science communication. And thirdly, in quite a number of the responses, without that being solicited, there was also the notion expressed that Academia Europaea could take a rather active, proactive stance on these matters. Which leads me to the third point, the establishment of the task force on a more permanent basis, which was decided based on the report from the analysis of the surveys about a year ago by the Board of Trustees. And I want to be clear about that. We have yesterday, when the new members were inducted, heard from the president about the mission of Academia Europaea, a set of important issues. In a sense, well, while remaining within this remit, I think what we are proposing, to which we'll come in a moment, is indeed pushing the boundaries of the mission of Academia Europaea, in the sense, namely, that what we identify, well, it's not that we identify that, but we focus on what you could call the ecological emergency of our times, and that we look towards transformative practices of Academia Europaea getting involved in developing transformative practices. This may not be the only emergency. We heard yesterday about other issues. We are aware of global emergencies, but this is the aspect we focused upon. And what the task force did in the next step, and that's the fourth step, is concretization. We looked at various aspects of this ecological emergency, also in relation to what other actions exist already, and indeed also what kind of evidence has been brought together recently on which one can build transformative practices. That's how we came to the choice of theme, which you see announced up there, namely healthy foods and sustainable agriculture, or secure and sustainable foodways, to summarize it in this term. We collected the recent evidence which was provided, and we elaborated a proposal. That would be the fifth step, and I give the word to Paul to present the proposal to you.
Right, thank you. Okay, so we had this workshop which had representatives of all the sections of Academia Europaea. We had a very full, engaging discussion, and of course the main question we raised is, why now and why Academia Europaea? The one driving force that really inspired us at the workshop was the conclusion of the SAPER report on food in 2020, which I'll read it out, states, food insecurity and sustainability are widely recognized as among the most significant global challenges facing humanity in the 21st century, linked to a range of other challenges, including malnutrition, biodiversity loss, climate change, soil degradation, and water quality. So, in a sense, food, which is such a mundane activity that we all engage in, which is an everyday phenomenon, generates welfare, sustains human life, health, but also generates all these problems that we are struggling with. So healthy foodways can be very dirty foodways. In many ways, food systems are really how we change the world, how we impact the environment. Every day when we as consumers make a choice, we decide what's the landscape going to look like? What is the future of biodiversity? How do we impact climate? So this is clearly something that needs to be addressed. And Academia Europaea has the opportunity now to, because of its actions, to set up a task force, to champion a high-level intervention based on a science-driven recognition of the need for global action. And the science is available in the SAPER report. It's also available in a host of other excellent reports, such as the one that recently came out by the German academies on agriculture. And taking action now will also highlight the potential societal role and need for academies. We can play a role not just being a cozy, safe space for academics, but we should step forward and bring our evidence-based insight into play. So what do we propose? We propose that this food system emergency needs intergovernmental intervention and a high-level action which also speaks to citizens, communities, NGOs, and businesses. So it needs to be an intervention at all societal levels. So a successful intervention must have these characteristics of having a clear, traceable, engaging measure of change. We need to be able to say, this is what we want to see change. It cannot be just arm waving. It needs to be clearly identified. It needs to build on established and trusted science. And it cannot be prescriptive in a way that we will preach to the world that there is only one way. It needs to embrace multiple pathways for transformative practices. So we propose that there is a need for what would be the third intergovernmental panel. We have, of course, an intergovernmental panel for for climate change, we have one for biodiversity, but we need a panel that will directly address the human interaction with the environment through our food choices and address the urgent need for food security in a world that is looking towards an increase of populations to perhaps 9, 10 billion people in the next 3 or 4 decades, which will increase the demand for food. But also, if we do not engage now, we will be on pathways that we know are detrimental to environment. So we need change. This intergovernmental panel must include all the sciences. If we want to be successful in achieving change, we need to call on engineering, we need to call on bioscience, we need to call on communication, societal policy intervention, and we need to talk to questions of culture. We need to have food literacy. And we also need to be able to monitor the change. We need to be able to develop research that actually monitors change, but we also need to have, for policy measures, clear indicators. And that's why we propose that we should have, as a guiding measure for the Intergovernmental Panel for Food Security and Sustainability, a single indicator for food security and sustainability. There are multiple measures available, but the single most negative factor of globalized food waste is without a doubt the very high meat component in affluent lifestyles. This is what is really impacting climate change and landscape deterioration. So when we measure this, the global human trophic level today is 2.28. What does that mean? Well, if we were plant eaters, if we were cows, we would have a trophic level of 2.0. If we were tigers, we would be up there at 5. Luckily, humans are omnivorous. We have a large plant-based diet, but we also have a meat consumption, which, because of our sheer numbers, have a hugely detrimental effect on the planet. So every little helps. If we could lower the human trophic level, that would be beneficial. And we certainly cannot foresee a future going into 2050, which is based on a human trophic level of 2.28. That would be absolutely catastrophic. So a reduction, not to a completely vegan diet, but even a reduction by 0.1 would have dramatic beneficial consequences for climate, biodiversity, landscapes, oceans, and human health. Now, we clearly need research to fully model what would be the impact of taking progressive steps towards a lower human trophic level. But there is no doubt that this indicator would be a very strong, powerful, and readily available instrument for us. It is already recognized by the United Nations Sustainable Development Goal for zero hunger. The human trophic level is a recognized measure for this, and the SDGs map the human trophic level across the globe, and you can see here, not surprisingly, the green countries, so apparently the ones that we should learn from, unfortunately also are the countries that most of them are struggling for nutritious foods. Africa. So it's not necessarily just a good thing to be green. The human footprint is lower, but unfortunately this human food security is low. So we need to combine security and sustainability. The two need to go hand in hand. But if we look at the future, many of the aspiring economies are looking to become redder, and that would be disastrous. So we need to encourage innovative ways of thinking about food ways. No one food culture fits all, but we can learn from each other. And increasingly, we value the diversity of cuisines. We don't need to go down the route of food shaming. Don't eat that. But we certainly need to have a much more balanced diet. And this could be not only at the intergovernmental panel, but it would also be hugely engaging for citizens. They could practice and develop healthy cooking. We envision developing an app or apps that would help you monitor your own food, and games that we could play in our cities, regions, countries to ensure that we know who are the winners, who are actually on the green pathway. So all of this comes with a potential for being built on science, addressing the intergovernmental level, but also be engaging at the citizen level. There we go. Next one. Excuse me.
So you might have recognized that I don't look like Verena, as per the slide. Unfortunately, Verena is really ill and has decided not to bring COVID into the conference, and that means that I'm going to be presenting her slides. I believe we started an experiment with the task force. So one result of that experiment is the content that Peter and Paul have just been explaining. And I'm going to just spend 2 minutes talking about observing the experiment from the viewpoint of the Academy itself. That experiment happens to be a task force on environment, sustainability, and climate. But should the Academy be doing more task forces? And if so, what and how? Let me describe what we think we've learned to date on that particular experiment. So to remind everyone, this time last year in Barcelona, people were invited to offer thoughts about what the task force should do and their enthusiasm in joining that task force. Following that, we decided to bring members together in what we call an efficient format to tackle the challenge that had been identified. So we ran a workshop. I think the answer to date is yes. Can Academia Europaea contribute uniquely, it's a really important word, uniquely, to challenge-driven scholarly work? And you will have seen already that we had one member from every section. We didn't load it and say, we understand the shape of the problem. We need every member who's an expert in the food system to be in a room. So we had people who are experts in music and communications, thank you, in the room, Helena. Why did we make that choice? Was that the perfect membership? I think we've learned lessons, probably no. But we decided to go in that extreme direction to run the experiment rather than follow a traditional format. And I think we've discovered that we can, given a certain amount of competent administrative support. Thank you, Bergen and Cardiff. If you're listening, really fantastic job. Thank you, the board, for offering the funds to support this and a few other resources that are mentioned on the slide. I think we can do really interesting things. That's us. I don't know if you see this slide very often. And this is what we're trying to do, bring together all of the parts of the Academy to see if we can do things that are transformative. These are tackling the biggest challenges of our time. So I'd like to say thank you to all the people who turned up. There's quite a few names on there, and they're from every section. And when we first gathered, we were sitting there going, I wonder why I'm here. Well, I mean, a lot of people going, I'm not an expert on food. It does seem to have worked, and I'd like to give some evidence for that with quotes. Sorry, Verena, I'm not a great lover of animation in slides, so I'm rushing through. You can pick your own quote. I'd like to take some statements out of this. This is how academies should become contributors to solving global problems. So there's a purpose dimension. So what is the Academy for in helping the world tackle great challenges? And how might we do that? But there's also another dimension to it. The members loved it. There's joy in some of those comments, and they would like to go back and do more. Spend it. You are an amazingly smart group of people, and being alone with you and locked away with you for 2 days, and learning you, watching you as you go into the depth of your topic and bringing your knowledge to bear on a meaningful problem is fantastic. It's not the same as this conference format. It's a very different format, but it is immensely rewarding and people would do it again. I think that's the comment. So I think this is something that the Academy can do for its members, as well as the members can do for society at large. So I think it's a really successful experiment, and I'd like to thank everyone involved and pass the microphone on to the real boss. Always.
Okay, so thank you very much. So we are really glad that that the Young Academy of Europe was also involved and invited to take part in this task force activities. So Scott Bremer, the former vice chair and actual also re-elected vice chair of the Young Academy of Europe, and me took part in the task force and in the preparation of this workshop. And it is also good to know that on the next event of Academia Europaea in the Wroclaw hub at the Anthropocene conference, Scott will present some of the outputs of this workshop and of the task force. And so I just show a few slides about how this format looks like. So it was surprising for everyone. So I mean, I'm also not really used to facilitated workshops, but we had a fantastic moderator in person of Steve. So he was moderating the event. So we were sitting around having all kind of sessions. We were divided then into subgroups. And in these subgroups, we were discussing different topics, developing ideas together, doing some kind of brainstorming, then getting together in the same room again, sharing our mind maps and explaining, summarizing all the outputs of the work of these various subgroups. So it was really interesting, and you see we've used plenty of flip chart papers, and we worked hard to try to find these solutions with which we came up finally. So I think everyone really enjoyed. It's a kind of really transformative and novel format. And so the last slide is about that if you are interested and would like to join the activities of the task force, you should contact Steve on his email address. And we will continue the work, or we would like to continue the work with 3 different kind of subgroups or groups in which, first of all, we will need to have a closer look again about the research-based evidence that is available, the current knowledge, not only to measure and wage the possible benefits, but also we should be aware and we should be careful with unintended and still unknown consequences of this proposition to change the human trophic level and to use it or not as a primary indicator. Then we would also like to work a little bit more closely about this intergovernmental panel for food security and sustainability. So how it is working, how it should work, how we should go forward with this idea. And we can use the experience of the intergovernmental panel on climate change, but the more recent one about biodiversity and ecosystem services could be also useful in this. Another subgroup could work on the communication. So we already did some things, and Paul mentioned that we should develop clear communication tools towards society, people, find out novel ways to get people, and especially those who are reluctant to change their these kind of things, or who are not engaged yet with these ideas. So we could use apps and games and similar things to communicate about these transformative practices in the food system. And of course, the most important is the financial plan. So we are grateful for, as Steve said, for the support of Academia Europaea, but we should find a kind of maybe other potential resources and possibilities to increase our progress. So thank you for your attention.
All right, we have about 1 or 2 minutes for comments. So very quick comments if anyone has it. Wait for the mic. Yeah, there you go.
Would you mind elaborating a little on the human trophic level? I didn't quite get how it's arrived at.
Yeah, okay, so the trophic levels is basically the primary production is, of course, well, you would think of grass, or in the ocean you would think of phytoplankton, and you move up the food chains. So a grass eater would be 2.0. Predators preying on other animals, the further up you move, you will enter up to a level of 5, where you would have the tigers eating other large animals that will again be predators on lower animals. So that's why humans, as omnivorous animals, we have a plant-based and meat-based diet, which globally amounts to a level of 2.28 at the moment. It's, of course, hugely varied across the globe. So in some countries, you will be much higher up. Those would be the red countries in the map, whereas other, especially poor countries, have an almost vegetarian diet. And if you look at it historically, you can see how Western countries have moved from a largely vegetarian diet into a more meat-consuming diet in the last 100 years. So meat is very much associated with welfare. And that's the problem, that a lot of our food cultures are predicated on quite wasteful energy consumption. So for every trophic level you move up, you lose 90% of energy. So you would get vastly more energy resources if you stay at lower trophic levels than for every time you move up. So if you are eating tuna, you are unfortunately eating into a level 5. So it's something to bear in mind. It's not, we don't propose this to be prescriptive, but it's something that needs to be worked into a balanced diet. And it could be part of, when you go to your cafeteria, that it could be clearly labeled, what is the trophic level of your food? Yeah, sorry. Anyone? Yeah, one last question, and then I'm afraid we need to move on.
Thank you very much. It was very interesting, and I want to congratulate you on your work up to now. As an economic historian, I would suggest that you take stock also of the knowledge about previous alimentary transitions in the world. I would just make two suggestions here. One is the fact that alimentary transitions take time. Certainly it's good to accelerate them, but you cannot do it from one day to another. And the second thing is that a strategic point would be to take into consideration how to avoid the trap between healthy food and cheap food. Because this is an important thing, and taking into consideration also the price in the choices of people is crucial. Thank you.
Yeah, thank you very much for that comment. I would just say briefly, first of all, you're entirely right. No one, sometimes one now thinks about human history in these larger terms as a series of transitions, and the agricultural transition is then one of them. And indeed, we have to look at that carefully. Maybe I just respond, for reasons of brevity also, by making the comparison to the climate change intergovernmental panel, where we now all are very familiar with the climate target of 1.5 or a maximum of 2 degrees Celsius of further global warming. But there was a long prior debate about that until this goal was reached. It was from the beginning, the starting assumption was that global warming is a problem, one has to do something about that. But then a lot of time was spent on elaborating exactly the facets and dimensions of the problem to then arrive at this indicator, which since then guides further debates. I think if this governmental panel on food security and sustainability comes into existence, and that's what we try to work for, there will be such a phase as well, where also relating to the earlier question, where the human trophic level will need to be spelled out more clearly, also in relation, that's your question, to historical earlier transitions. And there will be a phase of work which includes research in relation to then policy consequences. And at some point, maybe one arrives at this indicator or another one, but hopefully a single indicator, because that has the potential of focusing debates in terms of searching for solutions, as has happened with climate change. That's the ambition here.
Thank you so much, and that brings us to the conclusion of this part of the session. So thank you, and Stephen, you will stay here. And I need to make an apology. Unfortunately, I need, once I've introduced our next speaker, to just run out the door, because I have been told that in order to catch my plane, I simply need to be running. So, our final talk today, and Stephen has kindly agreed to then chair us through. Our final talk today is delivered by a prominent member of the Young Academy, Dr. Scott Bremer. He's a senior researcher at the Center for the Study of the Sciences and the Humanities at the University of Bergen. His background is in environmental governance, especially coastal governance, and more recently, place-based climate adaptation. So he wants to know how science and other knowledge systems can be used to support decisions and action in institutions at the science policy interface. So you will see that this is so very relevant to the previous discussion. A key question is how people come to understand climate variability and change in order to live with it. Bremer co-leads the Argus Alliance action called Engaged European Citizenship, and he is also the PI of the European Research Council Starting Grant Calendars project. The title of his talk is How Seasonal Cultures Shape Adaptation on Aotearoa, New Zealand's Coromandel Peninsula. Scott.
Thank you, Professor Holm. Thank you to the organizing committee. Thank you to Frederike again, as she's received a lot of those thanks these last 2 days. And thanks to those of you who are still here to the bitter end. I hope it's not only because I'm holding a big stick. I'll say what this is in a moment. It's really a privilege to talk in this aula. I mean, Newton said we stood on the shoulders of giants, I was thinking, and now I feel like I'm surrounded by them. So it's really there's a gravitas to being in this room. Helga Nowotny opened this conference talking about having and losing control in society at large, or at least the illusion of control. And now I'm going to kind of bring it round full circle to the end of this conference and talk about what it means for a small community in New Zealand on the Coromandel Peninsula and how they are particularly losing control of one of the most fundamental coordinates that helps them navigate the year, the seasons, the seasonal patterns and the seasonal coordinates. How do they go about acting seasonally when the long-held rhythms that organize the year no longer seem to hold? This talk is about how people navigate the changes in timings that come with climatic and environmental and social change. So in addition to moving from the very general to the very, very super specific of a tiny community, I'm also going to shift angle a bit. We've talked a lot about formal science. I'm thinking back to Tim's talk and Mona's talk yesterday. Now I'm going to be thinking about other ways of knowing. More embodied ways, tacit ways of knowing, things that we take for granted, like our seasonal cultures. The way we think, the way we act, the way we feel seasonally over the year, and how that is triggered at certain moments or encapsulated within particular seasonal repertoires that we give effect to each year, often unthinkingly. So before I go further, I should say that this was a project, the Calendars project, funded by the European Research Council, and that I have a whole team to thank, but I'll particularly thank Paul Schneider, postdoc, who's been working with me in New Zealand. So, this presentation is a stepping off point for a new line of research I want to pursue, a research program into adaptation as re-coordinating our cultural timings, our cultural frameworks, and our skills for using those frameworks. And when I talk about frameworks, I'm thinking of formal things like this here, Norwegian primstav, or the Gregorian calendar, but I'm also thinking about the very tacit, the very informal seasonal frameworks, our ways of acting seasonally that often go under the radar, so to speak, our ways of being. It's adaptation as kind of recalibrating these timings with a focus on seasonal cultures particularly, and in this case, we will look at how communities on the Coromandel Peninsula culturally interpret changes to local seasonality and how they choose to adapt their seasons. I begin by asserting that adaptation largely overlooks the particular capacity afforded to communities by their temporal frameworks and the ways in which they use them. If we look at some authoritative reports on climate adaptation, such as the IPCC's Sixth Assessment Report of last year, we see it's all quite implicit. Well, widespread deterioration of ecosystems, as well as shifts in seasonal timing, have occurred due to climate change with adverse socioeconomic consequences. And how do we respond? Well, governance practices will work best when they're coordinated within and between multiple scales and levels, institutional, geographical, and temporal. But it's all quite glancing. very little adaptation work really digs into the temporal, the timing that goes to adaptation. What is the right time to do what when? And so what a lot of scholars have said is that time in climate adaptation research, and arguably in environmental management and governance more generally, remains a linear coordinate. It's boiled down to clock time, and we look far back into the past and we project far forward into the future. We've had quite a few talks about that over the last 2 days. We project future climate change in 50, 100 years, but it's this kind of looking along one future line into the timeline and projecting climate change and rushing to prepare ourselves for that. But as Norbert and Pelling say, by looking constantly ahead, we've forgotten to question why we are looking so far ahead and what is surrounding us. We've forgotten to consider what are the timings that we're entangled in right now, right here in our lived moment now. So what I'm advancing is lowering our gaze from looking at climate change on the horizon to looking at the different times or temporalities we are enmeshed in now and how they morph and change and how we have to change our timings to resync with them. This has been the basis for an interdisciplinary field of study across the social sciences and humanities, and I quote Helge Jordheim and Espen Utreberg, who said that time should be considered in the plural rather than the singular has become a widely accepted fact in the humanities and social sciences, that time in social, cultural, and historical settings is always multiple, relative, and highly dependent on external factors. So this means departing from this single coordinate of clock time to recognize the multiple other temporalities, rhythms of change and motion that we're surrounded with. Our heartbeat, the tides, the diurnal rhythms of night and day. These are all rhythms which we are enmeshed in, and so I've taken the liberty of putting up an image well known to anthropologists by the well-known anthropologist Tim Ingold, where he talks about weather worlds, thinking of ourselves not as kind of coordinated by this single linear notion of time, but enmeshed in these times that are all around us, penetrating us, these bodily, earthly, and seasonal social cycles. And so, as another anthropologist said, these patterns of unintentional these temporalities, they bundle, they knot, they assemble into patterns that hold and then slip and then hold again. Patterns of unintentional coordination develop in polyphonic assemblages. To notice such patterns means watching the interplay of temporal rhythms and scales in the divergent lifeways that gather, says Singh. So if I use an example, here's a quote from one of the duck shooters that we interviewed in New Zealand. I dig my stick in the ground on the first weekend of May because that's duck shooting weekend and that's been a big part of my life for many years. And so there should be water in the wetlands. In the past, you could guarantee it more than now. In the old days, it used to be colder and I was aching for that morning sun to hit me, to even have my fingers in it. But I don't have that now. It's warmer. And then the ducks that we shoot on opening weekend, before we used to have a pattern. The ducks that you shot on a Saturday, you would start cleaning them on Sunday or Monday, but now they'd be going rotten. They'd be going green. So we clean them the same day. What you see in this short account of what is the duck shooting season or the opening weekend of duck shooting season is an assemblage. There's hydrological rhythms in there. There are social rhythms of the weekend and the weekday. There are practical rhythms of how to clean things and what to do when. There is climatological rhythms of night and of warm and cold. So I need to speed up. On that basis, we have been working from this above definition of seasonal cultures as individuals and groups perceived patterns and yearly rhythms that they segment into periods that are meaningful for them and affect practices that maintain or change these patterns. Perhaps I say 4 quick things about that. First of all, seasons are specific to places, but they're also specific to particular groups in a society. A duck hunter will track very different rhythms and act on a different assemblage of seasonal rhythms than an accountant or a hotelier or a barista. There are shared coordinates for organizing that group. While each individual duck hunter will have his own unique way of doing that first opening weekend, together there are some shared coordinates. Seasons are reproduced through practice. It's not just perceiving seasons, we reproduce those seasons. And they can be formalized in calendars, like this primstav, or they can be informal. Right, let's get moving. Let's leave Munich and let's go to the Coromandel Peninsula in New Zealand. It's a small peninsula, so if we flew into Auckland, we would drive about an hour and a half eastward to this peninsula where there are about 33,000 people spotted around 50 settlements, tiny little valleys, isolated by mountains. So you have these small kind of, microclimates, micro-environments, so that everyone actually experiences the seasons quite differently, even if they're only separated a few kilometers apart. Culturally, the meteorological calendar is split into 4, and those 4 seasons are split into 3 Gregorian months. March, April, May is autumn. June, July, August is winter, and so on. But there are many, many other cultural calendars on the peninsula besides. The indigenous people of New Zealand, had 43 different calendars before colonization. And 28% of people living in New Zealand now were not born in New Zealand. So it's a highly heterogeneous society with a great number of different seasonal calendars or cultures. Importantly, this study was a transdisciplinary study where we noted that only people who are engaged in a particular activity in a particular place can have this lived bodily experience and knowledge of these seasonal rhythms. And so for us, it was less a case of scientifically mapping these than working with the duck hunter, with the school teacher, with the others that we worked with to kind of together map out this kind of mesh of different seasonal patterns. So let's get to some of the interesting findings for the last 7 or 8 minutes I have. How do people perceive these seasons to be changing? Well, climatically, there have been some significant changes. There has been a warming, there has been a drying, and there are many, many more dramatic climatic events. Just this last summer, that's December, January of last year, there were 3 or 4 cyclones that chased each other's tails through New Zealand. And you can see they were washing away some of the main roads in that part of the world. So the climate, the regular climatic rhythms that people were used to, when the river would start running at a certain time of year, when the grass would get the rainfall it needs, that has been changing. Otherwise, we can look at environmental change. There's been a deforestation on the peninsula. And at the same time, as one of the farmers said, the fertility is going out of the land. The soil is very, very shallow, the hills are very, very steep, and so a lot of that farmland and farming was really kind of a key rhythm that was setting a tempo to community life on that peninsula. That farmland has started to go fallow or head back into scrub, to go back to scrub. We're losing a lot of animals. So one of the key markers of seasonality for Māori was birdsong. Particular migratory birds that would arrive at certain times of the year and would signal that a particular pattern of shellfish gathering, of fruit gathering, and other kind of livelihood strategies could begin. Those birds are leaving, and all we're left with are the nose flutes of the Māori that they made to mimic those bird sounds. Globalization and colonization. As one of our participants said, Pākehā culture, Pākehā's European culture, is characterized by our collective individualism. And so there is no group that feels authentic where you have seasonal celebrations. We haven't been brought up connected to the earth or to culture, except the culture of colonization. It just makes me feel really lonely. I love Matariki, and I'll say what Matariki is in a minute, because it's the beginning of really owning where we are. No one on the peninsula feels that there's an authentic seasonal culture anymore, including the Māori, because those birds that they used to tell time by have gone extinct. Those copse of forests, those small kind of clumps of forest and the rivers that used to run at certain times now no longer run. So they don't feel like their indigenous calendars are authentic anymore. And at the same time, European culture has imprinted their seasonal culture on New Zealand. And so we do strange things like spray paint snow in the windows at Christmas to emulate this kind of Christmas feel. And so in addition to colonization, we have this globalization of seasons, these images of the 4 seasons that is circling the world through films like our Christmas films that we watch each year. And so what this image shows here is some children, students that we took on a walk. We were doing a lot of working with different groups in the community, and we took them on a walk. And as they went underneath the manuka tree, the small white flowers that were there, it was December, and they shook this, and in an American accent they said, "Merry Christmas, Merry Christmas." So you can see these young people growing up with this idea that, wow, actually, Christmas is a time of snow, even though it's such an alien concept for us. And our changing relations to nature, the things that we notice, the ways that as one school teacher we worked with said, we're losing the habit of noticing. Young people are losing the habit of noticing the natural rhythms that surround us. What people that we talked to did say, though, is that they have 3 strategies emerged that people employed as they started to see their seasonal patterns start to slide and fall apart. On the one hand, there was this feeling of lock-in, that their institutionalized patterns were so deeply institutionalized and deeply rooted that it was impossible to change them anyway now. The school holidays was put forward as an example. January had ceased to be the warmest month, now it's become February. So there was talk about shifting the school holidays to February. But everyone said, no, but that's entirely impossible. How could we possibly fit in the 40 school weeks that we need? They couldn't see another way of arranging that within a year. Another nice example was put forward by the fire service, who said that they put a fire ban from Christmas until the rain starts again. And why was it Christmas? Was this something linked to the natural rhythms of when land dries out and things? No, he said, it's just because everyone goes on holiday at Christmas time. And so we just put this, we start the date then, and then we circle around and close the fire season once it starts raining again. So these kind of deeply rooted social patterns of holidays, school holidays, public holidays, structure things, and are so kind of anchored in the year that it's difficult for people to imagine changing seasonality anyway. Season proofing, see, I have 2 minutes left. Season proofing was put forward as another strategy. This is, of course, effectively withdrawing yourself from the seasonal pattern, from the vagaries of the season, from seasonal variability. It was about, for example, coupling your activities to the global market, so that now farmers start to produce their lambs in winter for the Christmas table in Europe. So the spring lamb is known, this kind of iconic symbol of the spring lamb is now no longer something that holds for farmers, or at least on the Coromandel Peninsula. Of course, infrastructure, water tanks. We don't need to worry about droughts, we just put in bigger water tanks. So we're just detaching ourselves from those things. But what was put forward, and this is my last slide, as the main strategy was to kind of reconnect with these changing seasonal patterns, these changing rhythms, whether they be social or natural in the ways they're intertwined, to find something that felt authentic for people wherever they'd come from, whether they were originally from Europe, whether they're freshly off the boat from Samoa or Norway or wherever, or whether they're Māori that have been there for 500, 600 years. And so it was something about attaching the seasonality, the ways we think and act and feel, to particular markers that were particular to New Zealand. So one new holiday in New Zealand now is Matariki. It's the Māori New Year, and it's attached to the Pleiades star constellation in June. Because this is one thing that Māori could not shake, this feeling of, it felt so strange that the year would begin in the Gregorian year in the middle of summer, when there's all this activity. This seems the wrong time for a year to begin. Most cultures internationally, the year begins out of this kind of the darkness of midwinter. Or, as two of our people were saying, to return back to the birds, to wait for the return of some of these migratory birds that come through and set a very nice, audible signal of different times when different seasons start, and as signals for different seasonal patterns of activity. And so I wanted to finish, if this will work, with the call of the shining cuckoo, which many people has attracted a great amount of attention in New Zealand. There are Facebook groups, there are all sorts of different social media platforms where people track the return of this shining cuckoo. It's very faint. The New Zealand bush is almost silent now. So if we can learn to retrack the natural rhythms through audible natural signals, through the stars, through bird calls, many people saw this as a route towards having more authentic seasonality. Thank you very much.
Thanks, that was very interesting. You said in your abstract that the third solution was the one which people thought the most, the best in the end, to adapt to the new. I mean, what will happen when this adaptation is not possible anymore? Like, say, it doesn't rain anymore at the end of the winter, the dry period, or something like that. I mean, what are your thoughts for this?
I didn't get to it, but people saw these seasonal frameworks, cultural frameworks of seasons, as something to cope with the variability between year to year, of course. So this kind of small maneuvers of being able to change and remain agile for small changes. Okay, the rains haven't come for 2 weeks later this year, so then we might plant a little later or so on. But also some really fundamental ways of rethinking how we seasonally pattern the year, starting to put new holidays in at different times, thinking of changing when we might send kids to school. These are much more fundamental adaptation things when a particular seasonal pattern now really has shifted so far out of phase that it's not enough to just shuffle around your practices and adjust to this temporal assemblage that you're nested in, that you need to really kind of reconfigure this seasonal thing. So I had up a destroyed road, and this is one of the main roads along the Coromandel Peninsula, and now they're saying, you know, I think we're not rebuilding some of these roads in New Zealand. A lot of these roads are just so at risk that they're not going to rebuild them anymore. So that would change patterns of movement, seasonally and otherwise.
Thank you.
Thank you for that. I'm not going to stretch any more questions. I, for one, am going to be thinking about time very differently. On this lovely, sunny summer's day in October, I'd like to bring the event to an end by calling up Don and Maria. And while we're doing that, can you please thank Scott?
So, dear colleagues, we have been celebrating during these past days science and researchers here in Munich, but we cannot ignore what has happened and what is happening in Israel and Gaza. Academia Europaea has over 85 members in Israel, and several of them came here, which we appreciate a lot. There were nevertheless other Israeli Academia Europaea members who signaled that they have to cancel their participation because they did not want or they could not leave their country under the current conditions. So I must admit that I don't have words to say more about this. But now I would like to turn to acknowledgements. And so once more I would like to congratulate the awardees of the 3 Academia Europaea prizes and the Mischke Prize of the Young Academy of Europe. I would like to thank the new members and the 4 members for participation. All the speakers, the chairs, the laudators, of course, are thanked, and Don, who has been the organizer of this event. And I also wish to acknowledge the organizing committee, which consisted of the 4 chairs of our 4 classes. So Don, your words.
Yes, so I want to echo everything that the President just said. Congratulations, Madam President, on a fantastic meeting under your aegis as President of the Academia Europaea. We hope that we'll be able to succeed as well next year as we did this year. We had about 320 plus participants and about 160 new members. As you know, it was a bumper year because of the 2 years that we had to recognize, or that we were grateful to be able to recognize as new members. I too want to thank the speakers. It was fantastic. Every talk I listened to was certainly an education for me and an enrichment. And I too want to thank my program committee, consisting of the 4 class chairs, for building this program in such a thoughtful and in such an intelligent way. So if they're all gone, I think at this point, I saw Paolo leaving. Björn is still here. So Björn Wittrock, Paolo Papale, Poul Holm, and Eva Condorosi really rolled out some high quality material for us this year, and it is their thoughtfulness which has led to the construction of the program. I want to thank the professional service of the Congress Centrum here at the University of Munich. They did their job admirably, and they reacted to all my panic attacks on time. And of course, I want to say again, thanks to Friederike Brandhaus and Sarah Straubinger, who are both here, who carried really the weight of the daily challenges in the last 90 days as we led up to this meeting. We will attempt a feedback mechanism for this meeting. So if you are contacted to ask about your impressions or your suggestions in the wake of this meeting, it would be a great help to us going forward in planning next year's meeting, wherever it may be. We expect to have a decision on where the meeting will be well before the end of the year, and you will all, of course, be immediately informed. Thank you very much for coming to Munich. God did his best with the weather, and we did our best with the room. We wish you all a very safe journey home without sickness or accident, and we look forward to seeing you at next year's meeting if you can attend. All the best.